Hello and welcome. Wherever you are right now, take a moment to pause. Maybe you're lying in bed, letting the weight of the day slowly melt away. Or perhaps you're resting on the couch, headphones on, searching for a voice to keep you company as the night unfolds. I want you to take a deep breath in and let it out slowly. Feel the air leaving your body, taking with it the stress of today. As you listen, you don't need to do anything. No need to keep your eyes open. No need to hold on to any thought. This is your time to simply relax, drift, and let your mind wander. Tonight, I'll take you on a journey far back into Earth's history. We'll explore some of the most terrifying, unimaginable, and extraordinary events our planet has ever endured. Times when the world was not the safe, familiar place we know now, but instead, hostile landscape shaped by fire, ice, and cosmic chaos. So as you listen, don't worry about remembering every detail. Let the words flow like a quiet river through your thoughts. Whether you drift off into sleep or stay with me until the end, this story is here to guide you calmly, gently through the hidden chapters of our world's darkest past. Are you comfortable? Are you ready to close your eyes and let curiosity lead you into the unknown? Then, let's begin. The earliest Earth as you settle deeper into your pillow. Let your mind drift backwards in time. Not decades, not centuries, not even thousands of years, but billions. Imagine the world before there were cities, before there were forests, before there was even life as we know it. Close your eyes and picture it. The Earth is young. It is only just formed from swirling clouds of dust and gas that circled our newborn sun. For a moment, try to see that violent beginning, the heat, the collisions, the endless impacts of space rocks raining down. The surface is not calm. It is oceans of lava stretching as far as the eye can see. Glowing rivers of molten rock carving through mountains that are not yet solid. Above the sky is a haze of smoke and fire. It's filled with ash and poisonous gases. This was the Hadean era, more than 4 billion years ago. A time when the Earth was nothing like the gentle home we know today. It was a planet under siege, its skin constantly torn open by volcanoes. Its atmosphere heavy with carbon dioxide, methane, and steam. And yet, even in this chaos, the foundations of everything to come were being laid. Breathe in slowly and imagine standing there, though no human could. The ground beneath your feet would tremble with every eruption. The air would scorch your lungs. And yet, above the fury, there would be beauty-towering fountains of lava lighting up the night, and a sky alive with constant flashes of lightning. The Earth was dangerous, but it was alive. Take another deep breath. Now, imagine the moon rising above this young planet. In those days, the moon was so much closer, looming huge in the sky, almost 10 times larger than it appears today. It had been born from a colossal collision when a Mars-sized body smashed into the Earth, tearing away fragments of rock that eventually gathered to form our lunar companion. The moon's pull was immense, creating tides in the molten seas, pulling at the very bones of the Earth. Can you see it? That giant, glowing orb hanging in the sky, watching silently over the chaos below. As you drift, remember our world's history is not just one of destruction, but also of transformation. Slowly, the oceans of fire began to cool. Steam condensed and fell as rain, not for days, not for years, but for millions of years. Imagine that rain, endless and unrelenting, carving valleys into the still soft crust, filling basins with the first true oceans. The sound of it must have been deafening, like the constant roar of waterfalls pouring from the sky, and with water came possibility. The oceans became a cradle, a vast chemical soup where the ingredients of life could slowly, quietly begin to combine. The storms raged above, the volcanoes still burned, but beneath the waves, something new was stirring. Now take a moment to relax your shoulders. Feel the weight of your body sinking deeper into comfort. As you breathe, let yourself picture those ancient seas, not blue and calm, but green, hot and filled with minerals. Imagine the faint spark of life beginning there, so small, so fragile, yet destined to shape the entire history of this planet. But before life could truly take hold, Earth would endure more trials. Entire ages of ice, when glaciers stretched from pole to equator. Entire ages of fire, when continents split apart and magma flowed across half the globe. And even visitors from the star's giant asteroids, slamming into the Earth with the force of millions of nuclear bombs, changing the course of evolution forever. Think about this. Every quiet night you experience, every gentle breeze, every calm ocean wave, it all exists because Earth survived those unimaginable trials. The calm you feel now is a gift from billions of years of chaos. So, as you listen, you don't need to worry about the science or the details. Just imagine. Let the images pass through your mind like dreams. The young Earth glowing red with lava. The endless rain that filled its oceans. The first fragile spark of life hidden beneath the waves. And above it all, the moon, watching silently, closer and brighter than you've ever seen it. As your breathing slows, let yourself wonder, what would it have felt like to stand at the edge of one of those first oceans? To hear the hiss of lava meeting water, to see lightning strike the surface, to watch steam rise into clouds that would rain for another 1,000 years. It is a world we can only imagine, yet it is the same world beneath your feet right now. The ground you walk on is forged from that fire. The water you drink has been raining down for billions of years. You are connected to that past in every breath you take. And so, as you drift deeper into rest, hold on to that thought. You are part of a story that began long before humans, long before animals, long before even plants. A story written in fire, ice, and stone. Tonight, we will travel through those chapters together. Now, allow yourself to let go of the present moment. The world outside your window can wait. For now, there is only this journey, this story of Earth, told gently, step by step, until your mind feels light and your eyes grow heavy. When you are ready, we will step deeper into the first great ages of terror, the times when Earth froze solid, when deadly rains fell, and when fire from the heavens reshaped everything we know. But don't worry, I'll be here to guide you calmly through each moment. Take one last deep breath and let it go. We are ready to begin. The future and the science of dreams. Dream research is also branching into unexpected territories. Some scientists are exploring how lucid dreaming, a state in which the dreamer becomes aware they are dreaming, could be used as a training ground. In lucid states, individuals can consciously manipulate their dream environment. This opens doors for athletes, musicians, or even pilots to practice complex skills in a risk-free setting. Experiments have shown that muscle memory and mental rehearsal can improve even when performed inside a dream, blurring the boundary between rest and training. Beyond skill enhancement, lucid dreaming may become a form of therapy. For patients suffering from recurring nightmares common in trauma survivors, lucid interventions can allow them to rewrite their dream scenarios. Instead of reliving the terror, they may consciously shift the story, giving themselves control and reducing emotional distress. If widely adopted, this could change how society treats conditions like PTSD, anxiety, or insomnia. On a broader cultural scale, the ability to guide dreams could transform creativity itself. History is full of examples where dreams inspired groundbreaking art and science. Mary Shelley's Frankenstein, Paul McCartney's Melody for Yesterday, and Dmitri Mendeleev's vision of the periodic table all reportedly came through dreams. Now imagine entire industries, filmmaking, music, literature being influenced by deliberately designed dreamscapes. Dream incubation tools could help creators step into their ideas and bring them back to reality more vividly than ever before. But There's a warning hidden here. If dreams can be designed, who decides what we dream? Just as social media shaped attention spans and information flow, dream technology could shape imagination itself. The commercialization of dreams might one day mean advertisements not only between YouTube videos, but also within our nightly subconscious. Picture a corporation planting subtle product symbols inside a user's dream. The ethics of such a possibility are deeply debated. But the fact that it's conceivable proves how powerful dream science could become. From a medical perspective, researchers are increasingly interested in how dream patterns may act as predictive biomarkers. For example, shifts in dream intensity or recurring imagery could be early signs of neurological diseases like Alzheimer's or Parkinson's, since these conditions often affect the brain decades before physical symptoms appear. Monitoring dreams could serve as a non-invasive diagnostic tool. Nightly reports from wearable devices may soon reveal whether the brain is moving toward illness, allowing interventions far earlier than current medicine allows. Another exciting branch of research looks at how dreams reflect emotional regulation. Neuroscientists propose that during REM sleep, the brain rehearses emotional scenarios in a safe environment, helping individuals process fear, grief, or joy. Dreams act as emotional simulations, preparing us for real-life challenges. This could explain why stressful events often appear in dreams not as exact replays, but as symbolic rehearsals. If we can decode these emotional patterns, psychologists may gain new tools to help people confront what they fear most, or to nurture resilience in the face of life's uncertainties. In addition, new brain imaging technologies are beginning to offer glimpses into dream content itself, while still primitive. Machine learning models can analyze neural activity and generate rough visual approximations of what a person is dreaming. The results are not crystal clear, more like abstract paintings than photographs. But the fact that any reconstruction is possible at all is astonishing. In the future, dream recording may allow us to replay our dreams or even share them with others. Imagine streaming your most beautiful dream, turning private fantasy into collective experience. This possibility excites some and terrifies others. On the one hand, sharing dreams could deepen empathy, allowing us to literally step into another person's mind. On the other, it could blur the boundary between inner privacy and public consumption. A dream is the most intimate theater of the mind, should it ever be exposed. This ethical dilemma mirrors larger debates in technology. Just because we can do something, should we? As we move further into this century, many futurists believe dream research will expand alongside artificial intelligence. AI systems already adept at generating art, music, and text may also simulate dreamlike experiences tailored to human minds. A personalized AI dream assistant could design nightly narratives optimized for relaxation, healing, or creative inspiration. Combined with brain-computer interfaces, such systems might allow humans to choose their dreams like one chooses a playlist. Sleep would no longer be passive. It would be curated, and yet, even as these prospects grow, one truth remains: dreams are deeply personal and mysterious. No matter how advanced the science, dreams often escape full explanation. They resist neat categorization, carrying fragments of memory, flashes of imagination, and echoes of emotion. This mystery is part of what makes them powerful. Dreams are the last frontier of the self, a space where science meets poetry, where neurons meet stories, where biology meets soul. Thus, the science of dreams isn't just about controlling or decoding them. It's also about respecting their role in human experience. They remind us that the mind is more than circuits and chemicals. Within its nightly wanderings lie clues to creativity, healing, and perhaps even the future of human consciousness. As research accelerates, we may find ourselves standing at a turning point. Will dreams remain private sanctuaries of imagination, or will they be harnessed as tools of medicine, art, and commerce. The answer will shape not only how we sleep, but also how we live. When we look toward the future, dreams may no longer remain confined to the hours of sleep. Instead, they could become integrated into daily life, blurring the line between waking reality and the subconscious. Emerging technologies suggest a world where people could enter dreamlike states on demand. Guided by neurostimulation, AI-driven narratives, and immersive virtual environments. This possibility leads us into a profound question. What does it mean to live a life that is part dream, part reality? One key area of research involves dream-to-waking continuity. The idea that the mind may use dreams as a rehearsal stage for waking decisions. If this is true, then the boundary between dreaming and reality is already porous. Future interfaces may make this continuity deliberate. Imagine slipping into a dream state before a big negotiation, practicing emotional responses in symbolic form, and then waking prepared to act with confidence. The subconscious would no longer be hidden, it would be an active partner in problem-solving dreams. May also become a new social frontier. Today, communication is bound by words, texts, and images. But what if future technology allows groups of people to synchronize their dreams? Shared dreamscapes could enable entirely new forms of connection. Instead of describing an idea, people could walk together inside a symbolic world shaped by their collective imagination. A classroom might not just teach history, might let students dream together inside ancient civilizations. A therapy group might share a symbolic journey, strengthening empathy in ways that ordinary conversation cannot. This prospect raises both excitement and alarm. On one hand, shared dreaming could dissolve loneliness, creating a sense of unity that transcends language and culture. On the other, it could threaten individuality, pressuring people to merge their inner lives with others. In societies where conformity is prized, dream sharing could become a tool of control rather than liberation. The power to guide not just what people think, but what they dream, is almost unimaginably strong. Philosophers have long wondered whether reality itself might be dreamlike. Plato's allegory of the cave, Descartes' famous doubt, what if life is but a dream? And countless spiritual traditions point toward the same mystery. As science grows closer to decoding dreams, these philosophical questions may gain new urgency. If dreams can be engineered, recorded, and manipulated, how can we ever be sure that waking life is not itself a designed simulation? The dream sciences may not just change our nights. They may shake the foundations of how humanity defines truth. Yet the future of dream research is not only philosophical light, is deeply practical. Consider mental health care. Depression, anxiety, and trauma are among the most urgent challenges of our age. If dreams act as natural rehearsals for emotion, then mastering them could provide relief for millions. Instead of simply prescribing medication, future doctors may prescribe dream therapies, guided lucid dreaming, targeted neurofeedback during sleep, or even AI-assisted dream mentors who help individuals reshape recurring negative themes into empowering narratives. This approach could reduce suffering while restoring dignity to the human mind. Dreams also hold potential in the fight against neurodegenerative diseases. Already, researchers are finding that disruptions in REM sleep precede cognitive decline. By studying dream activity in detail, scientists may learn to detect Alzheimer's or Parkinson's decades earlier than today. Preventative interventions could then be launched long before memory loss begins, preserving not just lifespan, but mind span for families across the globe. This shift could be nothing short of revolutionary at the same time. Creativity and innovation may undergo a golden age through dream technologies. Writers, artists, and inventors have always drawn from the subconscious, but now they may be able to harness it directly. An author could explore a dream library filled with infinite, unwritten books. A musician could wander through dreamscapes where melodies drift like rivers in the air. A scientist might dream inside molecular structures, uncovering solutions hidden in patterns too complex for waking thought. Humanity's collective imagination would expand beyond the limits of the waking mind. Yet we must also face the darker side. The commercialization of dreams is almost inevitable. If advertising already fills every waking moment, it may not stop at the threshold of sleep. Companies could one day pay for access to the dream state, implanting subtle imagery that guides consumer behavior. Even more troubling, authoritarian regimes could attempt to regulate what people are allowed to dream, shaping not just opinions, but imagination itself. In such a world, defending the freedom to dream may become as vital as defending free speech. Privacy, too, will be tested. With brain-imaging tools capable of reconstructing dream visuals, the question arises: who owns your dreams? Are they your private property, or can they be accessed by governments, employers, or corporations? The ethical frameworks we build today around data and digital rights may one day extend into the subconscious. Dreams, once the most intimate territory of the self, could become a battleground for autonomy in the 21st century. And yet, despite all these possibilities, utopian and dystopian alike, there is something about dreams that resists control. No matter how much we analyze them, dreams often surprise us. They speak in symbols, riddles, and emotions that cannot be fully measured by machines. This unpredictability may be our greatest safeguard. Even if technology encroaches, the essence of dreaming may remain wild, mysterious, and beyond total capture. Looking forward, humanity's relationship with dreams may define an entire era. Just as the printing press expanded knowledge, just as the internet reshaped communication, dream science could alter how we understand ourselves. It could bring healing to the sick, inspiration to the artist, clarity to the thinker. But it could also test the boundaries of ethics, privacy, and freedom. In this sense, the story of dreams is the story of humanity itself, always reaching for meaning, always balancing wonder with responsibility. Perhaps the most profound future lies not in controlling dreams, but in listening to them. Dreams are not random noise. They are conversations with the deepest parts of the self. They remind us that we are more than rational creatures. We are storytellers, symbol makers, wanderers through inner worlds. Whether recorded by machines or remembered in journals, dreams will continue to whisper truths that waking logic cannot capture in the end. As science advances, we may come to see dreams not as distractions, but as integral to what it means to be human. They connect us to memory, creativity, emotion, and even to the mysteries of consciousness itself. Whether used for medicine, art, or self-discovery, dreams will remain a bridge between past and future, between science and spirit, between the known and the unknown. And so, as we step into the next century, one question echoes: what kind of world do we wish to dream into being? The Hadean lava era, a world of fire. Close your eyes for a moment and try to imagine a world that feels nothing like the Earth you know. No oceans, no forests, no soft blue sky. Instead, the surface is a sea of fire, cracked open by endless rivers of molten lava. The air is not fresh and breathable, but heavy with poisonous gases, shimmering with the heat of constant eruptions. This was the Hadean time, when Earth was still young, raw, and violent. The name Hadean itself comes from Hades, the ancient Greek word for the underworld. And it is fitting, because to live on Earth then would have been to live in hell. Around 4.6 to 4.0 billion years ago, the planet was newly formed, born from the dust and rock left behind after the birth of the sun. But Earth's infancy was not calm. It was a battlefield. Countless asteroids and planet-sized objects collided with the surface, each impact releasing unimaginable energy strong enough to melt rock, boil entire oceans, and create craters hundreds of kilometers wide. During this chaotic period, Earth's crust was unstable, constantly cracking and reforming. Massive volcanoes erupted with no pause, spewing molten rock that covered everything in fiery flows. The surface was a hostile desert of lava fields, glowing rivers of magma, and towering plumes of smoke rising into a toxic sky. Lightning storms, fueled by volcanic ash, flashed across the atmosphere, while meteors rained down from space in a deadly bombardment known as the Late Heavy. Bombardment, it is hard to grasp just how extreme this world was. Temperatures at the surface soared high enough to melt metal. The very air shimmered with heat. If you were somehow able to stand on Earth back then, you would not see continents or oceans, only endless fire, molten plains, and seas of liquid rock stretching as far as the eye could see. The sky glowed red, thick with carbon dioxide and methane. The planet was wrapped in an atmosphere more like Venus today, suffocating, acidic, and deadly to any form of life we can imagine. And yet, this fiery chaos was not just destruction. It was creation. The violent eruptions brought materials from deep within Earth to the surface, forming the first primitive crust. The constant impacts from asteroids delivered not only energy, but also vital ingredients, minerals, metals, and perhaps even water locked in icy comets. The building blocks of life itself were being scattered onto this hellish stage, waiting for a calmer age to awaken. The Hadean Eon is also when the Moon was born. Scientists believe that around 4.5 billion years ago, a Mars-sized object called They collided with the young Earth. The impact was so immense that it blasted molten rock into space, where it slowly gathered and cooled into what we now see as the Moon. Imagine it, collision so catastrophic that it reshaped both Earth and the heavens, leaving behind a glowing satellite that would forever influence our tides, our nights, and even the rhythm of life. Despite the chaos, something remarkable was happening beneath the surface. As Earth continued to cool, heavy elements like iron and nickel sank downward, forming the planet's metallic core. This core, still molten today, generated the magnetic field that protects us from solar radiation. Without this hidden shield, life could never have survived in later ages. So even in its most violent youth, Earth was already preparing the conditions for a habitable future. But make no mistake, the Hadean was a nightmare realm. Oceans of lava stretched endlessly, broken by towering volcanoes taller than Mount Everest. Every day, the ground shook with quakes from asteroid strikes. Entire mountain ranges could be melted away in an instant. The Earth's surface was constantly remade, landscapes lasting not for millions of years, but for hours or days before being destroyed again. And above this fiery wasteland, the sky itself was terrifying. The sun shone faintly through a haze of ash and toxic gas, turning daylight into a perpetual twilight of red and orange. Thunderstorms raged endlessly, fed by volcanic particles in the atmosphere. Lightning flashed across the skies, striking the molten ground below, creating sparks that may have played a role in the first chemical reactions of life. When we call this era hellish, it is no exaggeration. For 600 million years, Earth was a world of constant destruction. And yet, from this destruction came foundation. The crust thickened. Oceans, though constantly boiled away, eventually began to form in small pockets. Water delivered by comets pooled into craters, cooling just long enough to survive before the next eruption. Slowly, painfully, Earth was shaping itself into a planet capable of holding life. This paradox, the world of fire giving birth to the conditions of life, reminds us that even in chaos, creation is at work. Without the lava flows, the asteroid strikes, and the fiery collisions, Earth would not have gathered the minerals, the atmosphere, or the Moon itself. What we think of as destruction was also construction. Out of fire came the possibility of oceans. Out of violence came the chance for peace. When you look up at the Moon tonight, remember, it is the scar of Earth's violent past. Its silent face, cratered and glowing, is a reminder of the Hadean Inferno. Each crater marks the same kind of impacts that once shook our planet to its core. And yet, those scars gave us tides, balance, and stability. The nightmare of fire became the foundation of the dream of life. As you listen to this story in the stillness of the night, imagine that distant world. The rivers of molten rock, the endless eruptions, the glowing skies. Let the image drift through your mind like a dreamscape, a reminder of how fragile and miraculous life is today. We live on a world that was once uninhabitable, unimaginable, and almost alien to us. And yet, here we are, breathing, sleeping, dreaming thanks to the very chaos that once made Earth a place of terror. So as you rest, think of the Hadean not only as an age of fear, but also as a promise that out of even the darkest and most violent beginnings, beauty can emerge. Out of fire, oceans. Out of chaos, life. Out of hell, a world that would one day cradle dreams like yours. Cryogenian snowball Earth, the world frozen solid. Now, let us journey forward in time to a world transformed by ice. The Hadean fires have cooled, the molten landscapes have hardened, and Earth has taken a more familiar shape. But nature has a way of surprising us, and soon, the planet would enter one of its most extreme chapters, the cryogenian period. Imagine a world where almost every surface, from pole to equator, is locked in a planet covered in glaciers, a snowball Earth. This period, occurring roughly 720 to 635 million years ago, is divided into two major glaciations, the Sturtian and the Maronanu. During these times, ice sheets stretched across continents, reaching even the tropics. Oceans froze over and snow accumulated relentlessly. The sun's warmth, though present, was no match for the planet's icy grip. Picture endless expanses of white stretching beyond the horizon, broken only by jagged mountains and the occasional volcanic plume pushing through the frozen crust. Life, already emerging in its simplest forms, faced unimaginable challenges. Microbial mats, the earliest life forms, had to survive under kilometers of ice or in isolated pockets of liquid water. The atmosphere was harsh, oxygen levels fluctuating, and nutrients trapped beneath thick sheets of ice. Imagine these early organisms struggling to persist, hiding in tiny refuges, waiting patiently for the ice to retreat. It is a world that seems inhospitable, yet life endured, adapting to conditions we can scarcely imagine. Think of standing on a frozen ocean, the ice cracking beneath you with each step. The wind cuts sharply, carrying the chill from poles that have never known warmth. The sun is a dim disk, barely penetrating the thick clouds above. Every movement echoes against the vast, icy silence. Snowdrifts stretch endlessly, and glaciers grind relentlessly against the land, reshaping continents in ways that will last for eons. The causes of this global freeze are still debated by scientists. Changes in the atmosphere, volcanic activity, and variations in Earth's orbit likely combine to plunge the planet into near-total ice coverage. Some theories suggest that the reflective white ice amplified cooling in a dangerous feedback loop, where frozen surfaces reflected sunlight away, intensifying the freeze. The result was a planet almost entirely encased in ice, a frozen shell that must have seemed eternal to any early life watching from beneath. Yet, as extreme as this ice age was, it to set the stage for the future. Beneath the frozen seas, volcanic activity continued. Heat from Earth's interior created pockets of liquid water, providing refuges for life. These hidden environments were crucial, allowing microorganisms to survive and evolve. In a paradox familiar from the Hadean fires, extreme conditions became the crucible of endurance. Life's persistence through snowball Earth laid the groundwork for the explosion of diversity that would follow in the Ediacaran and Cambrian periods. The planet's surface, Locked in ice also preserve unique geological markers. Glacial deposits, striated rocks, and dropstones tell the story of this ancient frost. Even today, scientists can read these clues to reconstruct the harshness of those global winters. They reveal a planet capable of swinging from extreme heat to extreme cold. A world of relentless natural forces. Imagine the oceans freezing over, layer by layer, until only thin cracks and volcanic vents allow water to move freely. The atmosphere is heavy, the light dim, and the winds relentless. For any creature or any single-celled organism, life required resilience beyond comprehension. And yet, slowly, imperceptibly, the planet began to change. Carbon dioxide from volcanic emissions accumulated in the atmosphere, gradually warming the world. Ice sheets began to retreat. Oceans thawed, and sunlight once again kissed the frozen lands. Life, having endured, emerged into a world reborn. As you listen, picture these vast frozen landscapes in your mind's eye. Snow stretching to the horizon, ice grinding against rock, volcanic plumes piercing the frozen skies. Imagine the silence, the cold, the alien beauty of a world that seems both deadly and mesmerizing. It is a reminder that Earth has been far more extreme than anything humans today can experience. And yet, these extremes were necessary. Without Snowball Earth, the evolutionary paths that led to complex life may never have been possible. Take a deep breath and feel the chill of that ancient ice in your imagination, knowing that underneath, life endured, hidden, patient, persistent. Think of the tiny microbial mats surviving against the odds, waiting for the thaw. They are the ancestors of everything that would come after the plants, the animals, the oceans, and even us. The cryogenian ice ages teach us something profound. Survival is not always about strength, but about endurance and adaptation. Earth's history is filled with periods of intense challenge, and yet life persists, reshaping itself, finding pockets of warmth and light even in the most inhospitable conditions. And now, as you drift deeper into relaxation, imagine standing on that frozen world, feeling the crunch of snow under your feet, the cold wind on your face, and the faint warmth from volcanic vents below. The planet may be frozen, but it is alive, humming with potential, waiting for life to flourish again. Let yourself float in this frozen landscape for a few moments. The world is silent, white, and vast. There is beauty in the extremes, lessons in survival, and wonder in the endurance of life. From the Hadean fires to the cryogenian ice, Earth has transformed dramatically, and each transformation brings with it the possibility of new beginnings. As you breathe slowly and deeply, allow the knowledge of these ancient extremes to wash over you. Feel the cold, the silence, the endurance, and the promise of life. And know that just as the planet survived its most terrifying frozen winters, so too can you find calm and rest tonight, cocooned in warmth and safety. Carboniferous rainforest collapse, the age of lush chaos now. We move forward in time once again to a period of life's exuberant explosion and dramatic upheaval. After surviving fire and ice, Earth had grown warmer and more stable. Vast forests spread across the land, creating a world of towering ferns, giant club mosses, and immense horsetails. Welcome to the Carboniferous period, roughly 359 to 299 million years ago. A time when life flourished like nowhere else, and yet, hidden dangers lurked beneath the greenery. Picture standing in one of these ancient forests. The air is thick, humid, and sweet, with the scent of decay and growth. Towering trees, some reaching over 30 meters tall, cast deep shadows on the forest floor. Massive insects buzz overhead, dragonflies with wingspans the size of modern hawks, millipedes stretching over 2 meters long. Everything is dense, teeming, and alive. You can hear the rustle of leaves, the creak of giant trunks swaying, and the distant rumble of storms approaching. These lush rainforests were not just beautiful, they were crucial engines of Earth's ecosystem. They produced oxygen in abundance, creating one of the richest atmospheres in history. Oxygen levels may have reached 35%, far higher than today's 21%, allowing insects and other arthropods to grow to extraordinary sizes. It was a paradise for life, a world of abundance and diversity unlike anything we see now. But paradise is fragile. Around the middle to late Carboniferous, the rainforest collapse occurred. A period of ecological upheaval that reshaped the planet. Climate changes, likely triggered by glaciation events in the southern hemisphere, caused rainforests to fragment. Large, continuous forests broke into isolated patches, leaving vast stretches of drier land in between. These shifts created a world of fragmented ecosystems, forcing species to adapt or perish. Imagine walking through what was once a dense, interconnected forest. The trees thin out, the air becomes dry and sharp, and the once bustling habitats shrink to isolated pockets. Many species, unable to migrate or adapt, vanish. The collapse leads to a drop in biodiversity, yet it also sets the stage for evolutionary innovation. Creatures that survive learn to navigate new landscapes, adapt to changing climates, and exploit niches that did not exist before. Survival becomes a test of ingenuity and resilience. In addition to climate shifts, other challenges made life precarious. Giant storms swept across these ancient forests, lightning igniting massive wildfires that could rage for days. Flooding rivers carved new paths through the land, uprooting plants and washing away animals. Earthquakes, triggered by tectonic activity as continents shifted, reshaped river valleys and mountains. Life in the Carboniferous was not only abundant, it was in constant tension with forces far larger and stronger than itself. Yet there is profound beauty in this chaos. The Carboniferous forests were also architects of our present-day world. The thick layers of plant matter that fell, died, and were buried over millions of years eventually became the coal beds that fueled human civilization. Every spark in a steam engine or light in a city owes something to the decay of these primeval forests. What once was alive, vibrant, and chaotic became a foundation for future energy and progress. The rainforest collapse also paved the way for the rise of new species. As dense forests gave way to open landscapes, early amniotes ancestors of reptiles, birds, and mammals found new opportunities to thrive. Fresh niches emerged and evolutionary experimentation accelerated. Life, always adaptive, turned catastrophe into opportunity. The collapse, though catastrophic for some, was a crucible for innovation and resilience. Imagine drifting through these ancient landscapes at twilight. The dense ferns cast long shadows, fog rolls across the forest floor, and massive insects perch silently among the branches. A river flows slowly, reflecting the muted orange of the setting sun, while distant thunder hints at an approaching storm. The world feels alive, mysterious, and a little dangerous. And yet, within this tension lies the profound miracle of life's persistence. The drive to survive and evolve against the odds. The Carboniferous period also reminds us of Earth's capacity for sudden transformation. From fire to ice, to dense forests and then drought-stricken collapse, the planet has continually reshaped itself. Each event, no matter how catastrophic, prepares the stage for the next era of life. Evolution thrives, not in comfort, but in challenge. Life's greatest achievements are forged in the crucible of adversity. As you listen, let your mind wander through these ancient forests. Feel the humidity, the rustle of ferns, the distant rumble of storms. Notice the interplay of abundance and danger, growth and decay. Allow the story of survival, adaptation, and transformation to guide your thoughts, easing your mind into the rhythm of this long-ago world. And here, in the stillness of your imagination, notice a lesson. Resilience is built slowly, often invisibly, through periods of both abundance and hardship. The Carboniferous forests, once lush and chaotic, remind us that life adapts, persists, and evolves, no matter how harsh the conditions. Even when vast collapses occur, life finds a way. So, as you rest, picture the endless green canopies, the towering ferns, the giant insects, and the fragmented forests after the collapse. Feel the pulse of life beneath your feet, in the soil, in the rivers, and in the creatures that survived. Let this vision of ancient abundance and resilience guide you into calm, restful awareness. The story of Earth's history, filled with extremes and wonders, reminds us that even in the face of immense challenges, life endures, so can you. The Great Oxidation Event, when oxygen became poison now. Let us move forward once again in our journey through Earth's most extraordinary events. Imagine a world that seems calm, oceans covering much of the planet, life already established in microscopic forms. Yet beneath this surface, dramatic transformation was about to occur, transformation that would both enable and threaten life itself. Welcome to the Great Oxidation Event, or GOE. Roughly 2.4 billion years ago, when oxygen first began to accumulate in the atmosphere. At first, oxygen was a strange and dangerous newcomer. Microbes called cyanobacteria, tiny but powerful, had learned to perform photosynthesis, a process that releases oxygen as a byproduct. For these early organisms, oxygen was simply waste, something to be expelled as they captured sunlight and converted it into energy. But for the rest of the planet, oxygen was a toxic intruder, a chemical capable of burning delicate molecules and poisoning cells that had evolved in an oxygen-free world. Imagine standing on early Earth. If you could somehow survive in this environment, the sky is hazy, pale, and filled with gases like methane and carbon dioxide. Tiny organisms float in the oceans, oblivious to the monumental shift they are about to cause. Every breath of oxygen is lethal to the anaerobic life that dominates the seas. For these early creatures, oxygen is no friend, it is a silent killer. As oxygen slowly accumulated, dramatic changes began. Iron in the oceans reacted with free oxygen, forming vast deposits of banded iron formations, colorful layers that today are mined as the world's iron ore. Entire ecosystems were reshaped, and many anaerobic species went extinct, victims of a gas that was harmless to some but deadly to others. The rise of oxygen was a planetary revolution, a chemical catastrophe for life as it had existed for billions of years. This event also triggered profound climatic and geological changes. Oxygen combined with methane, a potent greenhouse gas, dramatically altering the planet's temperature. Some scientists believe this contributed to the earliest known glaciations, plunging Earth into ice ages that may have lasted millions of years. Life, resilient but challenged, had to adapt quickly or perish. In this sense, oxygen was both creator and destroyer, a paradox woven into the fabric of Earth's history. But oxygen's rise was not only destructive, was transformative. The accumulation of free oxygen in the atmosphere allowed for the evolution of more complex life. Aerobic metabolism, which uses oxygen to extract far more energy from nutrients than anaerobic processes, became possible. This new energy potential set the stage for the eventual rise of multicellular organisms, leading billions of years later to the explosion of life forms that would populate the seas, skies, and eventually the land. Imagine floating above early oceans, seeing microscopic life evolving under the rising influence of oxygen. Cyanobacteria form mats across the seafloor, oxygen bubbles rising slowly to the surface. Life is struggling, dying, adapting, but in the process, it is also creating the conditions for the future. Oxygen is paradoxical, deadly in excess, yet essential for the energy transformations that make complex life possible. The GO also altered Earth's chemistry in lasting ways. Sulfur compounds in the atmosphere were oxidized, soils changed, and minerals formed in new ways. The stage was set for the continents to develop more complex soils, for nutrients to circulate differently, and for ecosystems to become more interconnected. Oxygen, the same gas that poisoned countless microbes, became a building block for an entire new era of life. As you drift deeper into this story, picture early Earth in your mind. Oceans shimmering with microbial life, clouds tinged with haze, volcanic activity punctuating the skyline. The air is changing, invisible yet transformative, carrying both danger and promise. The planet is alive, chemically dynamic, and unpredictable, teaching us that even a single molecule oxygen can reshape an entire world. Think of the paradox. Life creates its own challenge. Cyanobacteria, tiny and unassuming, release oxygen. Oxygen kills many existing species, but simultaneously creates the potential for more energy-rich metabolisms. Catastrophe and opportunity unfold together. The Great Oxidation Event is a story of struggle, adaptation, an eventual triumph, a chemical drama played on a planetary scale. By the end of this event, Earth's atmosphere had been transformed forever. Oxygen, once rare and deadly, became a central component of the air we breathe today. Yet we must remember the cost. Life had to endure mass extinctions, adapt to a poisoned environment, and evolve new strategies for survival. The Great Oxidation Event teaches a profound lesson. Evolution is not gentle. It is relentless, sometimes catastrophic, and yet, ultimately, creative as you listen. Allow yourself to imagine the silence of those ancient oceans, the unseen chemical battles taking place beneath the waves. Let the invisible rise of oxygen drift through your mind like a quiet, powerful tide, reshaping life from the inside out. Imagine the resilience required to survive, to adapt, to continue the thread of life despite a deadly new force entering the world. The GO also reminds us that Earth is a world of paradoxes. Life can both destroy and create. A single gas can be both a poison and a promise. Catastrophe and opportunity coexist, shaping every subsequent age. And this, too, is a lesson for us today. The challenges we face may be as transformative as they are threatening, and from them, resilience and growth can emerge. So, as you breathe slowly, picture the oceans of early Earth, the haze-filled skies, the rise of oxygen, and the small, persistent microbes that endured. Feel the paradox of creation and destruction, danger and potential woven together in the chemical heartbeat of the planet. Let the story of the Great Oxidation Event guide you gently into relaxation, reminding you that even in change and challenge, life persists in. So can your mind tonight. Permian-Triassic extinction, the great dying now. Let us move forward once again to one of the darkest chapters in Earth's long history. Imagine a world teeming with life forests stretching for miles, oceans filled with diverse creatures, the air thick with the calls and movements of countless species. Yet, a storm was coming, not of wind or rain, but of fire, gas, and planetary upheaval. This is the Permian-Triassic extinction, also known as the Great Dying, which occurred around 252 million years ago. During this catastrophic event, Earth lost approximately 90% of marine species and 70% of terrestrial vertebrates. Imagine entire ecosystems collapsing, coral reefs vanishing, forests dying, and the oceans turning into lifeless expanses. For creatures that survived, the world was unrecognizable, a shadow of its former richness. The primary cause of this extinction is closely linked to the Siberian traps, vast volcanic eruptions that covered millions of square kilometers with lava over tens of thousands of years. These eruptions released enormous amounts of carbon dioxide and methane, greenhouse gases that trapped heat and triggered rapid global warming. Temperatures soared to levels unbearable for many organisms. Oceans became acidic, and oxygen levels plummeted, creating dead zones where life could not survive. Imagine standing on the edge of a volcanic plain. Rivers of molten lava stretching into the horizon, the air thick with ash, and skies darkened by smoke. The heat is intense, oppressive. Toxic gases drift with every wind. In this hellish environment, survival is nearly impossible. Even small disruptions in temperature or oxygen levels become lethal. Life teeters on the edge of annihilation. The effects were not uniform. Some regions became deserts, others turned into swamps of stagnant, toxic water. Storms became more violent, weather unpredictable. Forests burned, sometimes for decades, releasing further carbon into the atmosphere. Oceans, once rich with life, experienced anoxia, the total depletion of oxygen. Fish, mollusks, and other marine animals perished in vast numbers. The cycle of death fed itself, creating one of the most severe planetary crises in history. And yet, as devastating as this extinction was, it also set the stage for the next chapter of life. The species that survived small, adaptable, and resilient would form the foundation for the rise of dinosaurs, mammals, and eventually complex ecosystems. In the chaos of the Great Dying, evolutionary innovation was born. Only life capable of rapid adaptation endured, teaching a timeless lesson about resilience in the face of catastrophe. Picture, for a moment, the oceans after the extinction. Vast, empty, and silent, except for the occasional survival of hardy microbes and small invertebrates. The coral reefs are gone, giant predators vanished, and the seas are eerily calm. On land, forests regrow slowly, patches of vegetation struggling to re-establish themselves. Creatures that remain are tiny compared to their predecessors, survivors of a deadly gauntlet that left only the fittest. The Siberian traps themselves are awe-inspiring and terrifying. Layers of basalt stretch endlessly, evidence of eruptions so vast they altered the planet's climate for millennia. Carbon dioxide and sulfur dioxide poured into the atmosphere, acidifying oceans, burning plant life, and creating extreme temperature swings. Lightning storms sparked from ash clouds, igniting fires across continents. Earth itself seemed to rage against life, reshaping ecosystems in a relentless, violent way. The Permian-Triassic extinction reminds us of the fragility of life and the immense forces that shape our planet. It shows how a single event, volcanic eruptions, greenhouse gas spikes, can ripple across the world, destroying habitats and species on an unimaginable scale. Yet it also demonstrates the resilience of life as surviving species adapt, evolve, and diversify in the aftermath. From devastation comes opportunity. From death arises renewal. As you listen, allow your mind to drift across this ancient, transformed world. Picture lava flows carving new landscapes, forests struggling to regrow, and the oceans slowly healing. Imagine the creatures that survived, small and adaptable, moving cautiously in a dangerous new world. Feel the tension, the heat, and the eerie silence of this planetary crisis. The Great Dying is more than a story of destruction. It is a testament to life's persistence. Even when nearly every species perished, life endured. Microbes, small plants, and tiny animals formed the foundations for new ecosystems. The Earth, despite extreme upheaval, continued to be habitable. And over millions of years, life would rise again, more diverse and resilient than before. So as you rest tonight, picture this ancient world. Imagine the fires, the ash-filled skies, the silent oceans, and the tiny survivors forging a path for the future. Let the story of the Permian-Triassic extinction guide you into reflection, a reminder of life's incredible ability to endure even the most catastrophic events. From fire and poison, from ice and collapse, life persists, and so can your mind tonight, calm and steady, drifting toward rest. Triassic Carnian pluvial episode, the rise of dinosaurs. Now, let us move forward into the Triassic period, approximately 235 million years ago, to a moment in Earth's history where climate and life underwent dramatic transformations. After the Permian-Triassic extinction, Earth was slowly healing, recovering from the devastation of the Great Dying. Life was fragile, yet resilient, slowly filling empty ecological niches. During this recovery, an extraordinary event occurred, the Carnian pluvial episode, or CP, a period of intense rainfall and climate change that reshaped ecosystems and paved the way for the rise of the dinosaurs. Imagine a world shifting from relative dryness to a wet, stormy climate. Torrential rains fell across continents, rivers flooded, and vast swamps emerged where deserts once prevailed. This period lasted for roughly 1 million years, a blink in geological time, but its effects were profound. Forests flourished in the newly humid conditions, creating lush environments teeming with ferns, cycads, and conifers. Swamps became breeding grounds for amphibians and early reptiles, while rivers teemed with fish and other aquatic life. The heavy rains and increased humidity created both opportunities and challenges. On one hand, ecosystems became more complex, supporting new forms of life. On the other hand, sudden floods and unstable habitats tested species adaptability. Extinction events occurred regionally, particularly among less adaptable groups. Yet, from this environmental stress emerged one of Earth's most iconic groups of creatures. The dinosaurs. Picture a lush floodplain. Mist rising from the wetlands, rivers carving winding paths through dense vegetation. Small, agile dinosaurs begin to appear, taking advantage of new niches. The first theropods, bipedal predators, stalk through the ferns, their keen senses alert to prey and danger alike. Herbivorous dinosaurs, like prosauropods, graze on tender shoots, their movements slow but purposeful. Insects buzz through the humid air, giant dragonflies hovering above the marshes. Life is thriving, but it is a delicate balance, with floods and storms constantly reshaping the landscape. The Carnian pluvial episode was not only a time of wet chaos, was a trigger for evolutionary innovation. Amphibians that dominated before were challenged by rising predators. Reptiles diversified, and the dinosaurs began their rapid evolutionary expansion. Early dinosaurs were relatively small, but their adaptability, speed, tactability allowed them to survive where others could not. Over the next tens of millions of years, these early pioneers would evolve into the towering, diverse dinosaurs we often imagine, from the massive sauropods to the fearsome seers. Meanwhile, other groups of animals responded differently. Some marine reptiles thrived in the warm, nutrient-rich seas, while certain amphibians and fish faced extinction in newly changing rivers and lakes. Plant life flourished under the humid conditions, expanding forest coverage and creating complex ecosystems. The interplay between climate, vegetation, and animal life during this time set the stage for the Mesozoic era, often called the Age of Dinosaurs. Imagine walking through one of these Triassic forests during a heavy rain. Mist rises from the ferns, dripping from enormous leaves. Small dinosaurs move quietly between trees, avoiding predators and searching for food. The air is alive with sounds chirps of primitive insects, rustle of leaves, and the distant calls of early reptiles. Every raindrop is a rhythm, a pulse in the ecosystem, reminding us that life is not static, but constantly responding to the environment. The Carnian pluvial episode also demonstrates the power of environmental change to shape evolution. Sudden shifts in climate can eliminate vulnerable species and open niches for new life forms. The dinosaurs, small and adaptable at first, exploited these opportunities, gradually becoming the dominant terrestrial animals for the next 165 million years. It is a lesson in patience, adaptation, and resilience. showing that survival depends on flexibility and the ability to exploit change rather than resist it. As you listen, picture the storms and floods shaping the land, rivers overflowing into forests, and small dinosaurs navigating the wet, challenging terrain. Imagine the first flight of pterosaurs gliding over marshes, the slow spread of early mammals, and the complex interactions of a newly dynamic ecosystem. Every element, the plants, the animals, the climates interwoven in a delicate balance of survival and opportunity. The Carnian pluvial episode, though only a brief moment in geological time, represents a turning point in life's history. It allowed dinosaurs to rise from humble beginnings to become the dominant terrestrial vertebrates of the Mesozoic. It reminds us that even brief periods of environmental upheaval can have long-lasting impacts, shaping the course of evolution in ways unimaginable to those living through it. And now, as you relax, picture this ancient world: rain-soaked forests, winding rivers, early dinosaurs moving cautiously through dense vegetation, insects buzzing in the humid air. The earth is alive, vibrant, and in motion. Life is emerging, adapting, and preparing for a future that will be both extraordinary and terrifying. Let the rhythm of the rain, the movement of creatures, and the pulse of the ecosystem lull your mind into calmness, knowing that even in times of chaos, life persists, evolves, and thrives. The Carnian pluvial episode teaches a profound lesson. Adaptation and resilience are the keys to survival. Life flourishes not in static perfection, but in dynamic change. From floods and storms, from extinction pressures and ecological stress, new possibilities emerge. The dinosaurs, small and nimble, represent this principle perfectly, showing us that the ability to respond to change determines the trajectory of life itself. As you drift further into rest, allow your mind to wander through these ancient, rain-drenched forests. Feel the wet earth beneath your feet, hear the distant calls of early dinosaurs, and imagine the slow, steady flow of rivers shaping the land. Life, despite adversity, continues. And in this meditation on survival and adaptation, find your own sense of calm, resilience, and peace tonight. Jurassic Cretaceous volcanic events and oceanic crises. Now, let us move forward once again into a period where the Earth's landscapes and oceans were being dramatically reshaped by fire and water. This is the time between the late Jurassic and early Cretaceous, roughly 160 to 100 million years ago, when massive volcanic events and oceanic crises transformed the planet, subtly setting the stage for future evolutionary changes. Imagine vast stretches of land dotted with erupting volcanoes, lava flowing across plains, and ash clouds reaching high into the atmosphere. The air is thick and heavy, carrying the scent of sulfur and heat. These volcanic events, though not as catastrophic as some earlier extinctions, had profound effects on the climate and ecosystems of the time. Carbon dioxide and other gases released into the atmosphere created periods of global warming, affecting both terrestrial and marine life. In the oceans, crises were unfolding silently, but with immense impact. Changes in sea level, shifts in ocean circulation, and decreased oxygen levels created what paleontologists call oceanic anoxic events. These periods saw vast regions of the seas depleted of oxygen, making them uninhabitable for many marine species. Imagine a once thriving ocean suddenly turning silent, the colorful reef ecosystems fading, and marine creatures struggling to survive in oxygen-starved waters. Volcanic activity also contributed to acidification of the oceans, as carbon dioxide dissolved into seawater, altering its chemistry. Marine organisms with calcium carbonate shells, such as mollusks and plankton, were particularly vulnerable. Entire populations declined, while other species adapted to survive in the altered environment. These subtle but pervasive pressures shaped evolutionary pathways, favoring organisms capable of withstanding environmental stress. On land, the effects of volcanic activity were equally significant. Forests were periodically blanketed in ash, and localized lava flows reshaped river valleys and plains. These disruptions created fragmented habitats where populations were forced to migrate, adapt, or die. Early mammals, small dinosaurs, and other terrestrial species faced new challenges and opportunities. Those that could move quickly find new food sources and cope with changing temperatures gained evolutionary advantages. Imagine walking through a Jurassic forest during this time. Ash drifts in the air. A faint red glow illuminates the horizon from distant eruptions, and the ground trembles subtly beneath your feet. Dinosaurs roam cautiously, some herbivores grazing among ash-covered ferns, while predators silently stalk through the changing landscape. Small mammals scurry in the undergrowth, their survival dependent on speed, awareness, and adaptability. Life is thriving, yet constantly challenged by the planet itself. The combination of volcanic activity and oceanic crises created a dynamic, sometimes unpredictable environment. Flooding lava flows altered drainage patterns, ash layers changed soil fertility, and periodic climate fluctuations stressed ecosystems. In the oceans, planktonic communities shifted in composition. Reefs were rebuilt repeatedly, and marine vertebrates, including early crocodiles and ichthyosaurs, had to adapt or migrate. Life's complexity and resilience were being tested continuously. Despite these challenges, the Jurassic-Cretaceous transition was also a time of great evolutionary opportunity. The disruptions created new niches, opening pathways for the diversification of dinosaurs, early birds, and marine reptiles. Coral reefs, though stressed, continued to rebuild in more resilient forms. Insects and plants evolved alongside terrestrial vertebrates, forming increasingly complex ecosystems. The interplay of environmental stress and biological innovation drove a subtle but profound transformation of Earth's biosphere. Imagine drifting above the oceans, observing ancient marine life navigating oxygen-depleted zones while volcanoes smoke in the distance. Imagine forests adjusting to periodic ash falls, rivers reshaped by lava flows, and animals migrating across fragmented landscapes. This is a world in flux, where survival depends on adaptability, where life is both fragile and astonishingly resilient. Oceanic crises during this period also remind us of the interconnectedness of Earth's systems. Volcanic eruptions affected climate, climate affected ocean circulation, and ocean chemistry influenced the survival of countless species. The planet's feedback loops, both chemical and biological, created challenges that life had to continuously navigate. It was a slow, almost imperceptible dance of adaptation, but the results were dramatic over millions of years as you listen. Allow your mind to drift through this ancient, transforming world. Picture volcanic ash drifting across plains, the faint smell of sulfur in the air, rivers redirected by flowing lava. Imagine marine life cautiously navigating oxygen-poor waters, dinosaurs moving carefully through ash-dusted forests, and early mammals seeking shelter in hidden niches. Life is persistent, dynamic, and ever-adapting. The Jurassic-Cretaceous period teaches us that gradual, consistent changes can be as powerful as sudden catastrophes. Volcanic events and oceanic crises may not wipe out entire ecosystems at once, but their long-term effects shape evolutionary trajectories, determine which species thrive, and prepare the stage for future ecological shifts. The resilience, adaptability, and innovation of life continue to shine, even under slow-moving environmental pressure. So, as you rest tonight, picture these ancient landscapes. Let the rhythm of distant eruptions, the flow of ash-covered rivers, and the silent pulse of oxygen-depleted oceans guide your thoughts into calm reflection. Life, despite its challenges, persists. It adapts, it thrives. And in this lesson from the Jurassic-Cretaceous transition, find a quiet reassurance, resilience, and change are part of life's enduring rhythm. And so can be your mind as you drift into peaceful rest. KPG extinction, Chicxulub impact, and Deccan traps. Now, we move forward to one of the most famous and dramatic events in Earth's history, the end of the Cretaceous period, roughly 66 million years ago. This is the story of the KPG extinction, the catastrophic event that ended the reign of the dinosaurs. It was a combination of cosmic and terrestrial, foresees the Chicxulub asteroid impact and the ongoing eruptions. Of the Deccan traps in India that reshaped life on the planet forever, imagine the Earth as it existed just before the impact. Dinosaurs roam vast forests, birds and early mammals scurry quietly, and oceans teem with fish and marine reptiles. The climate is warm, ecosystems are diverse, and life seems abundant. Yet, in the near future, a celestial object, a massive asteroid over 10 kilometers wide, is hurtling toward the planet, carrying unimaginable energy. The moment of impact is sudden and catastrophic. The asteroid strikes the Yucatan Peninsula in what is now Mexico, releasing energy equivalent to billions of atomic bombs. The ground shakes, shockwaves ripple across continents, and a fireball engulfs the surrounding land. The air is filled with debris and dust, blocking sunlight for months. Imagine the skies turning dark, temperatures dropping, and plants failing to photosynthesize. Life on the surface faces sudden and extreme challenges. At the same time, the Deccan traps are actively erupting. These enormous volcanic provinces in India release massive quantities of lava, along with carbon dioxide and sulfur dioxide. The combination of the asteroid impact and prolonged volcanic activity intensifies climate disruption. Acid rain falls across continents, oceans become more acidic, and temperatures fluctuate wildly. Ecosystems already stressed collapse under these combined forces. Marine life suffers dramatically. Plankton, coral reefs, and many invertebrates perish, disrupting food chains. Large marine reptiles, once apex predators, struggle to find sufficient food, and countless species go extinct. On land, the iconic dinosaurs, from the massive Tyrannosaurus rex to the towering Triceratops, vanish from the fossil record. Small mammals and birds, however, manage to survive, hidden in burrows, forests, or other safe niches. These survivors will eventually diversify and dominate the Cenozoic era. Imagine floating above the impact site in the moments after the collision. The Earth's surface is a blur of fire, ash, and smoke. Massive tsunamis radiate across oceans, engulfing coastlines. Lightning storms ignite forests, and volcanic gases drift globally. The planet seems momentarily uninhabitable, a testament to the raw, destructive power of cosmic forces. Yet even in this destruction, pockets of life endure. Tiny mammals burrowed beneath the surface, early birds seek shelter, and life finds a way to persist. The KPG extinction illustrates the interplay between multiple catastrophic factors. While the Chicxulub impact is often considered the primary trigger, ongoing Deccan traps eruptions likely exacerbated environmental stress. The release of greenhouse and acidifying gases, combined with sudden darkness and cooling from the impact, created a planetary double punch, wiping out species unable to adapt. Those that survived were generally small, flexible, and capable of coping with rapid change. Visualize the immediate aftermath on a global scale. Sunlight is blocked, temperatures fluctuate, and rainfall becomes acidic. Forests collapse, rivers overflow with debris, and oceans lose oxygen. Life is challenged in every corner of the globe. Yet over thousands and millions of years, Earth slowly recovers. Flora returns, ecosystems stabilize, and mammals, birds, and flowering plants rise to prominence. From the ashes of disaster, new forms of life emerge. The Chicxulub impact also left lasting geological evidence. A layer of iridium-rich clay, deposited worldwide, marks the boundary between the Cretaceous and Paleogene periods. This smoking gun tells the story of an extraterrestrial object colliding with Earth, forever altering the planet's trajectory. Combined with lava flows and gas emissions from the Deccan Traps, these events illustrate how Earth's geology and cosmic influences are deeply intertwined. As you listen, picture the drama of that moment, a glowing fireball descending from space, oceans surging with tsunamis, skies dark with dust, and life struggling to survive. Imagine the resilience of tiny creatures that will ultimately thrive, shaping the evolutionary future of the planet. This event is a profound reminder of the fragility and adaptability of life. Even when nearly all surface species vanish, life endures in hidden, resilient forms. The KPG extinction teaches us that catastrophic events can reset the course of evolution. The end of the dinosaurs allowed mammals to flourish, leading millions of years later to the rise of humans. It is a story of destruction and renewal, of endings and beginnings, of resilience in the face of overwhelming odds. The Earth, despite near-total devastation, continues its cycles of life, adaptation, and renewal. As you rest, allow your mind to drift across this ancient, turbulent world. Picture the asteroid impact, the glowing lava of the Deccan Traps, and the silent forests slowly recovering from fire and darkness. Imagine small mammals and birds cautiously emerging, exploring a new world in which the dominant species of the past are gone. Let the rhythm of this transition from destruction to recovery guide your thoughts into calmness, reflection, and a sense of peaceful awe. The KPG extinction reminds us that life's trajectory is shaped by both chance and resilience. It demonstrates the power of catastrophic events, but also the enduring potential of survival and adaptation. From this ancient collision and volcanic fury, a new chapter of life began, one that eventually leads to the world we inhabit today. And now, as you breathe slowly and gently, imagine Earth itself healing, ecosystems rebounding, and life quietly persisting as your own mind drifts toward rest. PETM, Paleocene Thermal Maximum now. Let us move forward to a time much more recent in geological terms, approximately 56 million years ago, during the Paleocene transition. This period is known as the Paleocene Thermal Maximum, or PET, and it provides a fascinating example of how Earth can experience rapid, extreme climate change. Unlike sudden catastrophes such as asteroid impacts or massive volcanic eruptions, PETM was a period of gradual but extremely rapid warming, with profound consequences for life on the planet. Imagine a world already recovering from the KPG extinction. Mammals have begun to diversify. Forests cover much of the land, and oceans teem with life. The climate, however, is about to shift dramatically. During the PETM, global temperatures increased by 5 to 8 degrees Celsius in just a few thousand years of geological heartbeat. Polar regions that were once icy or temperate became warm. Forests expanded poleward, and tropical climates spread into higher latitudes. This rapid warming had dramatic impacts on both terrestrial and marine ecosystems. Forests expanded into new regions, but species that could not tolerate the heat faced local extinction. Early mammals, including small primates and hoofed animals, adapted quickly, some migrating to cooler areas, others evolving new traits to survive in hotter, more humid climates. Imagine lush forests stretching toward the poles, with early mammals exploring new niches, insects buzzing in warmer air, and rivers flowing steadily through verdant valleys in the oceans. The warming had equally profound effects. Increased temperatures reduced oxygen levels in some regions, creating oceanic anoxic zones similar to those seen during earlier crises. Marine life, including plankton, mollusks, and early fish species, had to adapt or migrate. The chemical composition of seawater changed as large amounts of carbon were released into the atmosphere and oceans, likely from sources such as methane hydrates, volcanic activity, and organic carbon burial. These changes altered nutrient cycles, food webs, and overall ecosystem dynamics. Visualize drifting above the planet during this time. Warm winds sweep across continents, carrying humidity from newly expanded tropical forests. Rivers meander through lush valleys, supporting a diversity of plants and animals. Early mammals venture into unfamiliar regions, cautiously exploring as predators and competitors navigate the shifting environment. Life is adapting rapidly, responding to a climate that seems both generous and unforgiving. The PETM also demonstrates the interconnectedness of Earth's systems. As temperatures rose, ice-free polar regions allowed new ocean currents and atmospheric patterns to develop. This, in turn, redistributed heat and moisture across the globe, influencing rainfall, river flow, and plant growth. Ecosystems were constantly adjusting, with species moving, adapting, or facing extinction depending on their flexibility and resilience. It was a dynamic, ever-changing world, where the pace of change tested the limits of life. Imagine the contrast between ancient tropical forests and the higher latitude regions. Plants and animals that had previously only existed in warm climates now colonize areas closer to the poles. Small mammals, early primates, and newly evolved herbivores explore these expanded habitats, while insects and other invertebrates rapidly exploit new ecological opportunities. Life flourishes in some areas, declines in others. Reflecting the uneven effects of rapid climate change, PETM is a crucial lesson in how quickly life can be challenged by warming. While not as catastrophic as asteroid impacts, the rapid temperature rise caused shifts in species distributions, extinction events, and evolutionary pressures that shaped the future of mammals and marine life. Some groups thrived, adapting to hotter climates, while others dwindled or disappeared. It is a story of both vulnerability and resilience, demonstrating the importance of adaptability in the face of environmental stress. As you listen, allow your mind to drift through this warm, dynamic world. Picture forests expanding into higher latitudes, rivers winding through lush valleys, and early mammals navigating newly hospitable lands. Imagine the oceans warming and shifting, with plankton blooms and marine migrations responding to changing chemistry and temperature. Life is both challenged and thriving, a constant dance of adaptation and survival. The PETM also reminds us of the long-term consequences of rapid carbon release. The massive influx of greenhouse gases drove warming, altered ecosystems, and reshaped evolutionary pathways. Small mammals diversified, leading to new lineages that will eventually give rise to modern groups. Forests and wetlands expanded and contracted in response to changing rainfall and temperature, leaving geological and fossil records that tell the story millions of years later. As you relax, picture the world during the PETM. Warm oceans stretching toward the poles, forests teeming with early mammals and insects, and life responding creatively to rapid environmental change. Let the rhythm of this warming world guide your thoughts into calm reflection. Life, despite challenges, adapts, survives, and thrives. And as you drift toward rest, allow this lesson from the past to offer reassurance. Change is constant, but so is resilience, both in nature and within your own mind. The Paleocene thermal maximum, though occurring tens of millions of years ago, speaks to the power of climate to shape life. It shows how rapid warming can drive evolution, migration, and adaptation, and how life, even in the face of global challenges, finds a way to persist. Allow your mind to rest in this awareness, calm and steady, like the world recovering and thriving during that ancient warming episode. Supereruptions, Toba and other mega eruptions. Now, let us turn our attention to one of the most dramatic and awe-inspiring forces of nature, supervolcanoes. These are not ordinary eruptions, they are planetary-scale events that can shape climates, ecosystems, and even human history. Today, we explore mega-eruptions with a special focus on the famous Toba eruption, along with other colossal volcanic events that have left lasting marks on Earth's geological and biological history. Supereruptions are defined by their sheer scale. Unlike typical volcanoes that release hundreds or thousands of cubic kilometers of lava and ash over years, supervolcanoes erupt hundreds to thousands of cubic kilometers of magma in a single event. Imagine an eruption so vast that it blankets entire continents in ash, darkens skies for months, and triggers a temporary global cooling known as a volcanic winter. The consequences are immediate and long-lasting. One of the most well-known supereruptions occurred approximately 74,000 years ago at Toba, located in what is now Indonesia. The eruption released an estimated 2,800 cubic kilometers of volcanic material, making it one of the largest eruptions in the past 2 million years. Ash spread across much of South Asia, and the sky darkened with fine volcanic particles. Imagine days without direct sunlight, temperatures dropping sharply, and ecosystems across continents struggling to survive in sudden cold and darkness. The Toba eruption likely had global effects on climate. Scientists suggest that the massive injection of sulfur dioxide into the atmosphere may have cooled the planet by several degrees Celsius for years, disrupting plant growth and food chains. In human history, this event may have dramatically reduced populations, creating what is sometimes referred to as a genetic bottleneck, though evidence is still debated. The eruption illustrates the profound impact that a single geological event can have on life, climate, and even the trajectory of species. Other supereruptions in Earth's history were equally dramatic. The Yellowstone caldera in North America, the Campi Flegrei near Naples, and the Taupo volcano in New Zealand have all produced eruptions of staggering magnitude. Each of these events released enormous volumes of ash, lava, and gas, reshaping landscapes and affecting ecosystems far from the eruption site. Imagine entire forests buried under ash, rivers blocked by lava flows, and skies darkened for months, forcing wildlife to adapt, migrate, or perish. Supereruptions are not merely destructive, they also play a role in geological renewal. The deposition of volcanic material enriches soils, creating fertile plains over time. Lakes and calderas form in the collapsed volcanic craters, providing new habitats for aquatic and terrestrial life. Ecosystems gradually recover, and life finds a way to persist, adapt, and flourish in the long-term aftermath. This cycle of destruction and renewal is a recurring theme in Earth's history. Imagine floating above a supervolcano during the moments of eruption. Lava fountains jet into the sky, ash clouds spread thousands of kilometers, and pyroclastic flows rush down mountainsides at incredible speed. The ground trembles beneath your feet, rivers overflow with mud and debris, and the horizon glows with molten fury. Yet, amid this catastrophic scene, life persists in hidden corners. Small mammals burrow underground. Birds take refuge in distant forests, and aquatic life in distant lakes remains sheltered from the worst of the chaos. The ecological consequences of supereruptions extend beyond immediate destruction. Volcanic ash can remain suspended in the atmosphere for years, blocking sunlight and leading to cooler global temperatures, a phenomenon known as volcanic winter. Photosynthesis slows, plant growth declines, and food webs are disrupted. Animals face starvation, migration pressures, and increased competition. It is a world of stress, adaptation, and survival, where only the resilient and flexible endure. Supereruptions also remind us of the delicate balance between catastrophe and opportunity. While they can cause near-term devastation, they also create conditions for ecological innovation and long-term evolutionary change. New habitats emerge. Nutrient-rich soils foster plant growth, and isolated populations evolve into new species. In this sense, supervolcanoes are both destroyers and creators, reshaping Earth's biological and geological landscapes simultaneously. Imagine the aftermath of Toba or a Yellowstone-scale eruption. Vast ash-covered plains stretch to the horizon. Forests slowly recolonize regions once buried under meters of volcanic material. Rivers carve new paths through lava fields, and wildlife cautiously returns. Early humans or mammals explore these renewed landscapes, encountering challenges and opportunities alike. Life is persistent, adapting to the altered terrain and eventually thriving once more. As you listen, picture the planet during and after these colossal eruptions. Feel the tremors beneath your feet, the ash drifting silently through the air, and the quiet resurgence of ecosystems in the weeks, months, and years that follow. Life endures, even in the face of overwhelming natural forces. The cycle of eruption, destruction, and renewal is a reminder of resilience, adaptability, and the enduring rhythm of Earth itself. Supereruptions like Toba offer a profound perspective. Earth's forces operate on a scale far beyond human comprehension, yet life finds a way to persist. They remind us of the interplay between catastrophic events and the adaptability of species. Life survives not because it is impervious, but because it is capable of enduring change, exploiting new niches, and persisting even when the world seems inhospitable. As you drift toward rest, imagine this ancient world, supervolcanoes erupting with immense power, ash drifting across continents, and life slowly adapting to altered climates. Let the rhythm of Earth's cycles, eruption, destruction, recovery soothe your mind. The planet has faced unimaginable forces and yet continues to thrive. In this awareness, find calm, reflection, and reassurance. Life persists, adapts, and flourishes even in the wake of the most dramatic natural events. Historical volcanic winters, Tambora and Krakatoa. Now, we shift our focus from ancient supereruptions to events that occurred within human history, yet whose impacts on climate and life were profound and far-reaching. These are the famous volcanic winters triggered by eruptions such as Mount Tambora in 1815 and Krakatoa in 1883, while not on the same scale as supervolcanoes like Toba. These eruptions dramatically affected the climate, agriculture, and daily life, reminding us that even modest volcanic events can have global consequences. Imagine the world in the early 19th century. Societies are primarily agrarian, dependent on predictable weather patterns to grow food. Suddenly, Mount Tambora, located in Indonesia, erupts with unimaginable force. In April 1815, it released over 150 cubic kilometers of volcanic material, the largest eruption in recorded history. Ash and sulfur dioxide shot high into the atmosphere, spreading around the globe and reducing the amount of sunlight reaching the Earth's surface. The immediate effect was a year without summer in 1816. Crops failed across Europe and North America, leading to food shortages and famine. Snow fell in June and July in parts of the northern hemisphere. Rivers froze, and persistent cold and rainfall altered ecosystems temporarily. Imagine villagers tending fields under gray skies, snow in midsummer, and livestock struggling to survive. Humanity, though resilient, faced challenges that few had anticipated. The Tambora eruption also triggered dramatic atmospheric phenomena. Sunsets and skies turned vivid shades of red and orange due to scattering of sunlight by volcanic aerosols. These hauntingly beautiful skies were documented by artists and poets, yet behind this beauty lay suffering. Crops failed, food prices rose, and entire communities faced starvation. The eruption serves as a vivid illustration of how volcanic activity can influence climate, ecosystems, and human societies simultaneously. Less than 70 years later, another catastrophic eruption struck. In August 1883, Krakatoa exploded violently, producing one of the loudest sounds in recorded history, heard thousands of kilometers away. Ash, pumice, and volcanic gases were ejected into the stratosphere, creating a temporary global cooling of approximately 1 to 1.5 degrees Celsius. While smaller than Tambora in volume, the eruption caused enormous tsunamis and widespread destruction in the surrounding regions. Imagine villages along coastlines suddenly submerged by towering waves. While skies darkened with volcanic ash, Krakatoa's eruption provides insight into the dual nature of volcanic impacts: immediate destruction and longer-term climate effects. The towering tsunamis killed tens of thousands, while the ash and gases altered weather patterns globally. Sunlight dimmed for months, temperatures fluctuated, and the delicate balance of local ecosystems was disrupted. Both humans and wildlife had to adapt to these temporary but severe changes in their environment. In both cases, Toba and Krakatoa remind us of the interconnectedness of Earth's systems and society. Volcanic eruptions in one region can alter climate patterns thousands of kilometers away, affecting agriculture, health, and social stability. Crops fail in Europe due to an eruption in Indonesia. Monsoons shift. Winters become harsh or unpredictable. These events illustrate how fragile human societies can be in the face of natural planetary hysteria. Forces visualize the aftermath of these eruptions. Villages shrouded in ash, rivers clogged with debris, and skies painted with fiery sunsets. Farmers struggle to grow crops, livestock graze on sparse vegetation, and human communities adapt to a temporarily altered world. Meanwhile, wildlife navigates ash-covered forests and rivers, some thriving, others facing hardship. Life is forced to adjust rapidly, demonstrating resilience and ingenuity in the face of sudden change. Volcanic winters also offer lessons for modern times. They show how relatively localized events can have global consequences, reminding us that Earth's systems are deeply interconnected. They highlight the role of the atmosphere, sunlight, and ocean currents in distributing the effects of a single eruption across the globe. In Tambora and Krakatoa, humanity experienced firsthand the subtle but dramatic consequences of volcanic activity. As you drift through this historical perspective, imagine the vivid skies of post-eruption years, red sunsets, dimmed sunlight, and cool summers. Picture humans coping with unexpected cold, crops failing, and communities adjusting to unpredictable weather. Simultaneously, wildlife adapts quietly, rivers flow through ash-strewn valleys, and life, resilient and persistent, continues onward. The lessons of Tambora and Krakatoa echo through history. Even relatively short-lived events can leave lasting impressions on climate, ecosystems, and civilizations. The impact of volcanic winters goes beyond immediate destruction. They alter atmospheric composition, influence weather, and disrupt food chains, demonstrating that Earth's dynamic forces operate on multiple scales simultaneously. Life, both human and non-human, faces challenges and adapts, illustrating resilience, adaptability, and the subtle interplay between catastrophe and recovery. As you relax and listen, imagine these historical events unfolding in slow motion. See the world beneath the sky dimmed by volcanic ash. Feel the cool summer air. Hear the distant rumble of eruptions, and visualize life adapting in countless ways. Let the rhythm of history, the cycle of eruption, climate disruption, and recovery soothe your mind. Humanity and nature alike endure, adapt, and flourish, even in the face of temporary yet profound upheaval. Tambora and Krakatoa, though separated by nearly 7 decades, share a common story: volcanic power reshaping climate and life. They remind us of the fragility of ecosystems and societies, but also of the persistence of life, the ingenuity of humans, and the resilience of nature. As your mind drifts, allow these lessons from the past to guide you into calm reflection and peaceful rest. Limnic eruptions and Lake Nyos. Now we turn our attention to a fascinating and rare geological phenomenon: limnic eruptions. Unlike volcanoes or asteroid impacts, limnic eruptions occur in deep volcanic lakes, releasing massive quantities of gas that can suffocate life around them. One of the most famous examples took place at Lake Nyos, Cameroon in 1986. A tragic event that shocked scientists and local communities alike. Imagine a serene lake nestled in a volcanic crater, surrounded by lush mountains and dense forests. Lake Nyos appears calm and peaceful, reflecting the sky like a mirror. Yet beneath its surface, a deadly secret accumulates slowly over decades. Carbon dioxide, released from magma beneath the lake, dissolves in the cold, deep water. Normally, this gas stays trapped at the bottom under high pressure. But when conditions align, the gas can erupt suddenly. Like opening a shaken soda bottle, producing a massive, invisible cloud. On August 21, 1986, Lake Nyos released an estimated 1.6 million tons of carbon dioxide in a matter of minutes. The gas flowed like a silent, invisible tsunami down the valleys, displacing the air and suffocating nearly 1,700 people, along with countless livestock. Imagine a calm morning suddenly turned deadly, with communities overwhelmed by a dense, unseen cloud. There was no warning, no fire or explosion, just a quiet, creeping danger. Limnic eruptions are unique because they are non-explosive in the traditional sense, yet deadly due to the invisibility and density of carbon dioxide. Heavier than air, the gas hugs the ground, spreading into low-lying areas where people and animals reside. Survivors often describe the eerie silence, the sudden cold sensation, and the lack of visible threat. Life, both human and animal, is powerless against this unusual natural disaster. Scientists studied Lake Nyos extensively after the tragedy, discovering that other crater lakes in volcanic regions could pose similar risks. The combination of deep volcanic lakes, accumulated gas, and sudden destabilization creates a perfect natural trap for deadly carbon dioxide release. Imagine hundreds of lakes around the world quietly accumulating gases, the potential for sudden, lethal eruptions hidden beneath placid waters. The Lake Nyos event highlights how Earth's dangers are not always loud or dramatic. Unlike eruptions or earthquakes, a limnic eruption is silent, invisible, and fast. A reminder that nature's threats can take many forms. Humans, accustomed to visible disasters, can be blindsided by these subtle yet deadly events. It also emphasizes the importance of monitoring and preparation in geologically active regions. The impact of Lake Nyos was immediate and devastating. Entire villages were evacuated or abandoned. Survivors lost family, homes, and livestock, and the psychological toll was immense. However, scientific intervention followed. Engineers installed degassing systems to gradually release carbon dioxide from the lake safely, reducing the risk of future eruptions. Imagine the delicate process of controlling a natural force invisible to the eye, a testament to human ingenuity responding to the challenges of nature. Limnic eruptions also remind us of the diversity of planetary hazards. From asteroid impacts to supervolcanoes, from climate shifts to limnic gas releases, Earth presents dangers on every scale. Some are dramatic and immediate, others subtle and hidden, yet all can reshape life, ecosystems, and human communities. Life persists by adapting, surviving, and preparing for the unexpected. As you drift through this story, picture the calm surface of Lake Nyos, the dense gas slowly accumulating below, and the moment of sudden release. Imagine the invisible cloud creeping down the valleys, the eerie silence, and the way life is challenged in an instant. Let your mind follow the processes beneath the lake, the dissolved gases, the pressure and the careful scientific measures designed to prevent future tragedy. It is a world where danger and ingenuity coexist, where vigilance and understanding allow life to persist. The Lake Neo's disaster also teaches humility in the face of natural processes. No human effort can prevent all disasters, yet knowledge and preparation can mitigate risks. By studying limnic eruptions, monitoring lakes, and applying engineering solutions, humanity adapts to the subtle but lethal threats of the planet. Nature is vast, powerful, and often unpredictable. Yet we find ways to live alongside it. As you relax and visualize this serene yet potentially deadly lake, allow your mind to absorb the lessons of patience, awareness, and resilience. The world is full of hidden dangers, yet life continues, quietly and persistently, finding ways to endure. The silent power beneath Lake Nyos is a reminder that Earth's forces operate on many levels: visible and invisible, dramatic and subtle. Life in all its forms navigates these forces with remarkable adaptability. Finally, as you breathe slowly and calmly, imagine the restored balance of Lake Nyos, a safe, monitored lake, ecosystems rebounding, humans and wildlife coexisting with the forces of nature. Let this visualization guide you into peaceful reflection, the rhythm of Earth's hidden powers harmonizing with your own breath, leading toward calm, rest, and a sense of serene understanding. Mega tsunamis and other impact scenarios, Redafor and beyond. Now, let us journey into a world of cosmic collisions and their dramatic consequences on Earth. Throughout our planet's history, asteroid and comet impacts have shaped landscapes, influenced climate, and even altered the course of life. Among the most striking phenomena resulting from these impacts are mega tsunamis and other catastrophic effects, as exemplified by events like the Vredefort crater in South Africa and other colossal impact sites around the globe. Imagine a calm ocean stretching to the horizon, the sun reflecting off the water's surface. Suddenly, from space, a massive asteroid descends with unimaginable speed. Upon impact, energy equivalent to millions of nuclear bombs is released, displacing water, soil, and rock. In an instant, a mega tsunami is born, a wall of water hundreds of meters high, racing across coastlines, obliterating everything in its path. The sheer scale of these events is almost impossible to fathom. Yet the geological record tells us they have occurred multiple times throughout Earth's history. The Vredefort impact, which occurred roughly 2 billion years ago, is one of the largest known impact craters on Earth, with an original diameter estimated at over 300 kilometers. While far removed from human history, the scale of the event reshaped continents, generated massive shockwaves, and likely influenced the planet's crust and atmosphere. Imagine the Earth trembling, mountains collapsing, and rivers rerouted as molten rock and debris were expelled across vast regions. Life at the time, simple microbial and algal forms, experienced profound environmental stress. Yet even these earliest life forms persisted, demonstrating resilience against cosmic catastrophe. Mega-tsunmis are another dramatic outcome of large impacts, particularly those hitting oceans. When a massive asteroid strikes water, it displaces enormous volumes, creating waves that travel thousands of kilometers. Coastal regions are inundated almost instantaneously, with destruction extending far beyond the immediate impact zone. Imagine the sudden rise of water, sweeping forests, plains, and settlements into chaos, while the sky fills with debris thrown upward by the colossal force of the collision. Such events, though rare, demonstrate Earth's vulnerability to extraterrestrial forces. Other notable craters, such as the Chicxulub impact linked to the extinction of the dinosaurs, and smaller craters around the world, reveal the diversity of consequences following cosmic collisions. Impacts can generate not only tsunamis, but wildfires, atmospheric dust clouds, acid rain, and long-term climate change. These chain reactions affect ecosystems far beyond the initial blast, influencing evolution, species survival, and the trajectory of life on Earth. Picture entire forests ignited by re-entering ejecta. Skies darkened for months, and ocean temperatures and chemistry altered temporarily, forcing adaptation on a massive scale. Mega tsunamis and impact-related disasters highlight the interconnectedness of Earth's systems. The initial kinetic energy of an asteroid or comet is converted into shock waves. Water displacement, atmospheric disturbances, and ecological stress. Humans, wildlife, and even microbes must respond to these changes. Some perish, some migrate, some adapt. Life's persistence in the wake of these catastrophic forces is a testament to resilience, flexibility, and the continuous interplay between destruction and recovery. Imagine observing one of these events from a safe distance. The horizon shimmers as a colossal asteroid enters the atmosphere. Upon impact, a cloud of dust and vapor rises tens of kilometers into the sky, blocking sunlight and cooling the planet. Waves surge across oceans, inundating distant coastlines with almost unimaginable force. Forests, rivers, and plains are temporarily erased from the landscape. Yet beneath the surface, life clings on: microbes in the soil, deep-sea organisms in their refuges, and resilient species poised to repopulate once the immediate devastation subsides. Mega-TSUN-AMIS are not just ancient history. Geological evidence shows that large impacts in the oceans and near coastlines have occurred repeatedly, creating layers of sediment and fossils that tell stories of catastrophic flooding. Understanding these events helps modern science anticipate the potential consequences of future impacts and highlights the importance of planetary monitoring and disaster preparedness. Imagine the effort to detect and study near-Earth objects, the global coordination required to prevent or mitigate an impact, and the delicate balance between cosmic chance and human foresight. The Vredefort and other impact scenarios remind us that Earth's hazards are both terrestrial and extraterrestrial. While volcanoes, earthquakes, and climate shifts challenge life from within the planet, cosmic events present sudden, unpredictable dangers from beyond. Mega tsunamis, in particular, combine elements of both: the suddenness of a cosmic strike and the far-reaching effects on terrestrial and aquatic ecosystems. Life endures by adapting, migrating, and evolving resilience to these dramatic forces. As you listen, imagine the oceans roiling under the force of a cosmic collision, the sky filled with dust and fire, and waves racing across distant continents. Picture species responding in countless ways, some surviving by fleeing to higher ground or deeper waters, others succumbing to the immediate force. Life, despite vulnerability, continues. The interplay between catastrophic events and the persistence of life is a rhythm repeated across billions of years of Earth history. Mega-TSUN-AMIS and impact-related scenarios also underscore the scale of time and perspective. While a single event may seem catastrophic in human terms, life on geological timescales has repeatedly endured, adapted, and flourished. Microbes, plants, and animals rebound, evolutionary pathways shift, and ecosystems recover. From the Vredefort impact billions of years ago to ocean-striking asteroids more recently, Earth demonstrates both fragility and resilience, chaos and continuity. Finally, as you relax and visualize these cosmic forces at work, allow the rhythm of destruction and recovery to soothe your mind. Imagine the oceans, mountains, and forests slowly regaining balance after a mega tsunami, life repopulating the land, and the planet continuing its vast, ancient cycles. The story of impacts reminds us that Earth is a dynamic, ever-changing world where forces both terrestrial and cosmic shape the course of life. Life persists, adapts, and thrives even in the face of unimaginable power. Genetic bottlenecks, humanity, and the Toba debate. Now, we turn our attention from ancient oceans and mass extinctions to a more intimate, yet equally dramatic aspect of Earth's history: genetic bottlenecks. These are periods when populations of organisms, including humans, are reduced to remarkably small numbers, leaving lasting imprints on genetic diversity. One of the most widely discussed and debated bottlenecks in human history is associated with the Toba supereruption, which occurred approximately 74,000 years ago. Imagine the world as our early ancestors knew it: vast forests, savannas, and rivers teeming with life, humans living in small groups, hunter-gatherers moving across continents. Suddenly, the Toba volcano on Sumatra erupts with catastrophic force, ejecting over 2,800 cubic kilometers of material into the atmosphere. The ash and sulfuric aerosols disperse globally, dimming sunlight, cooling the climate dramatically, and creating a volcanic winter that lasts years. The world becomes colder, harsher, and less predictable, a formidable challenge for any species. Some scientists propose that this eruption may have triggered a human genetic bottleneck, reducing the global population to perhaps only a few thousand individuals. Imagine our ancestors facing starvation, harsh climates, and diminished resources. Survival is no longer guaranteed. Groups are scattered, isolated, and forced to adapt in any way possible to endure this sudden planetary stress. In such a scenario, the genetic diversity of humanity would shrink, leaving a profound imprint that we can detect even today in our DNA. The Toba bottleneck hypothesis is both fascinating and controversial. Genetic evidence shows reduced variation in human mitochondrial DNA, suggesting past bottlenecks. Yet, some studies question whether Toba alone could have caused such a dramatic reduction, arguing that early humans may have found refuges in Africa, South Asia, and other regions. Imagine small communities huddled around sources of food and warmth, surviving against seemingly insurmountable odds, while others perished unnoticed. The debate reminds us of the delicate interplay between geological events and biological survival. A bottleneck has profound evolutionary consequences. When populations shrink drastically, genetic drift becomes a dominant force. Rare alleles may disappear, and previously common genes may fluctuate unpredictably. This reduces diversity, but can also accelerate adaptation, as surviving lineages carry traits that allow them to thrive in the post-crisis environment. Imagine the survivors of Toba spreading across continents, carrying a smaller but resilient pool of genetic information, ultimately shaping the future of our species. The Toba eruption also highlights the connection between Earth's dynamic forces and human evolution. Volcanoes, climate change, and environmental stress influence not just the survival of species, but the genetic structure of populations. Humans are uniquely sensitive to these changes, dependent on resources, technology, and social structures to endure. Picture small bands of humans navigating ash-covered landscapes, adapting hunting strategies, and sharing knowledge essential for survival. The very behaviors that define our species. Interestingly, the Toba event may have indirectly accelerated human innovation. Surviving a global crisis could have reinforced social cooperation, technological ingenuity, and cognitive flexibility. Perhaps it was in these moments of extreme stress that humans began to develop more sophisticated tools, language, and strategies for communal survival. Imagine early humans huddled around fires, sharing knowledge, observing the sky, and planning for the unpredictable future. The interplay of catastrophe and adaptation is a powerful driver of evolution beyond humans. Genetic bottlenecks occur across the tree of life. Species from large mammals to microbes experience similar population reductions due to environmental disasters, disease, or resource scarcity. These bottlenecks leave lasting signatures in DNA, affecting diversity, adaptability, and long-term survival. Picture populations shrinking, recovering, and evolving a new life, constantly adjusting to the challenges imposed by planetary forces. The Toba debate also emphasizes the uncertainty inherent in interpreting Earth's history. Fossil records, genetic data, and geological evidence provide pieces of a puzzle, yet gaps remain. Scientists reconstruct scenarios with care, imagining the world as it may have been, humans navigating ash-covered landscapes. Ecosystems, stressed but resilient, life adapting to global perturbations. It is a reminder that understanding the past requires both evidence and imagination, a delicate balance between certainty and possibility. As you relax and visualize this chapter of human history, picture the quiet perseverance of our ancestors. Small groups surviving in scattered refuges, adapting to cold climates, limited food, and environmental stress. Imagine the intimate challenges of daily life, gathering resources, maintaining warmth, avoiding predators, and nurturing the next generation. Through these struggles, life persisted and humanity endured. Carrying forward the genetic legacy of survival, genetic bottlenecks like Toba are a testament to the resilience and fragility of life simultaneously. Populations can shrink dramatically, yet survivors carry the seeds of future generations. Traits essential for survival become encoded in DNA, shaping adaptation for millennia to come. The story of Toba is a story of life's persistence against overwhelming odds, of resilience emerging from crisis, and of evolution driven by both catastrophe and opportunity. Finally, as you drift through this tale, imagine the world slowly recovering from the Toba eruption, climates stabilizing, landscapes regenerating, and human communities spreading across continents once more. Let the rhythm of survival, adaptation, and continuity guide your mind into calm reflection. Humanity, like all life on Earth, persists through cycles of challenge and renewal. Even in the darkest times, life endures, adapts, and carries forward, quietly and resiliently, into the unfolding story of our planet. Oceanic oxygen loss, anoxic events, and their impacts on life. Now, we journey into the depths of the ancient oceans, exploring a phenomenon both subtle and catastrophic: oceanic anoxic events. These are periods in Earth's history when vast portions of the oceans lost nearly all oxygen, creating inhospitable environments for most marine life. The consequences of these events ripple through ecosystems, climates, and the evolutionary trajectory of life, reminding us that even the life-sustaining oceans can become sites of profound crisis. Imagine the oceans as vast, blue reservoirs of life, teeming with organisms from the tiniest plankton to the largest predators. Oxygen, dissolved from the atmosphere and generated by photosynthesis, allows this complex web to thrive. But during anoxic events, oxygen levels plummet, sometimes entirely disappearing from deep or even widespread regions of the oceans. The result is a silent, invisible threat, suffocating life beneath the waves. One of the most famous anoxic events occurred during the late Devonian, roughly 360 million years ago. Large portions of the oceans became anoxic, possibly triggered by rapid organic matter deposition, climate shifts, or nutrient imbalances. Fish, trilobites, and countless marine invertebrates faced suffocation, creating mass extinction pressure. Imagine entire marine ecosystems slowly collapsing, coral reefs dying, and oxygen-dependent organisms struggling for survival in murky, stagnant waters. Anoxic events often coincide with climate warming. Warmer waters hold less dissolved oxygen, and nutrient-rich runoff from continents can trigger explosive growth of plankton, which then die and decompose, consuming what little oxygen remains. This creates a feedback loop, expanding oxygen-deprived zones. Picture the ocean's once vibrant blue turning dark, layers of dead plankton and sediments accumulating, and life retreating toward the remaining oxygenated refuges. The planet itself becomes quieter, slower, and more hostile to previously thriving species, Another significant anoxic event occurred during the Cretaceous period, known as the Cretaceous Oceanic Anoxic Event 20AE2. Global temperatures rose, sea levels shifted, and oxygen-poor waters expanded across continental shelves. Life adapted in some regions while disappearing in others. Marine ecosystems were reshaped, with species migrating, evolving, or vanishing entirely. Imagine coral reefs bleaching and collapsing, plankton communities shifting, and early marine reptiles or fish navigating waters that were deadly in large swaths of the ocean. The consequences of anoxic extend beyond marine life. As oceans become oxygen depleted, carbon cycles are disrupted. Organic material that normally decomposes slowly begins accumulating in sediments, creating layers rich in hydrocarbons precursors to the oil and gas deposits we extract today. These events leave a geological record preserved in black shales. That allows scientists to study past crises and understand the interplay between climate, chemistry, and biology. Imagine the quiet accumulation of these sediments over millions of years, storing a history of crisis in the layers of the deep sea. Anoxic events also highlight the interconnectedness of Earth's systems. Changes in temperature, nutrient influx from rivers, and biological activity can tip the balance of oxygen availability in oceans. Life responds in complex ways. Some species die off, some adapt to low oxygen conditions, and others migrate to survive. This interplay creates both vulnerability and opportunity, shaping evolution in subtle but profound ways. Imagine life navigating these invisible stressors, some species flourishing in refuges, others vanishing. The oceans constantly reshaped by chemistry and climate. Visualize the ocean during an anoxic crisis. Beneath a calm surface, vast regions of water lack oxygen entirely. Dead organisms drift silently, forming layers on the ocean floor. Survivors cling to oxygen-rich pockets, adapting, evolving, and surviving against the odds. The ocean's surface may still teem with life, but below, an invisible thread reshapes ecosystems on a massive scale. It is a world of hidden danger, quiet suffering, and subtle yet relentless transformation. Anoxic events remind us that Earth's life support systems are dynamic and fragile. Oxygen, essential for most life, can vanish in large regions if conditions change rapidly. Life endures through adaptation, migration, and evolution, but the process is neither gentle nor predictable. Entire ecosystems may disappear, food webs collapse, and evolutionary pressures create new opportunities for resilient species. This is nature operating on a scale beyond human perception, yet with consequences that shape the planet's future. As you listen, picture the oceans in their moment of crisis. Dark waters, silent depths, struggling life, and slowly accumulating sediments. Allow your mind to trace the cycles of oxygen depletion and recovery, the slow but persistent renewal of marine ecosystems, and the resilience of life. Imagine the subtle rhythm of survival. Some species perish, some adapt, and life continues, quietly and persistently. Beneath the surface, anoxic events also connect to modern concerns. Today, human activity has accelerated oxygen depletion in some coastal regions, creating dead zones that mimic ancient anoxic conditions on smaller scales. By studying past events, we gain insight into resilience, adaptation, and the potential consequences of disrupting delicate planetary balances. The ocean's history teaches us to respect their complexity and fragility, understanding that life is intricately linked to the invisible chemical and physical processes that sustain it. Finally, as you relax, imagine the deep, quiet recovery of the oceans after an anoxic event. Oxygen gradually returns, ecosystems rebuild, and life slowly reclaims the depths. The cycle of crisis and renewal is a fundamental rhythm of Earth's history. As you drift into rest, let the story of these hidden oceanic crises remind you of the resilience of life, the subtle power of natural forces and the delicate balance that sustains our world. Even in the darkest depths, life adapts, persists, and flourishes once more. Scientific tools for Earth's history: isotopes, sedimentary records, and drill cores now. We shift our focus from dramatic natural disasters and human survival to the scientific tools that allow us to uncover Earth's deep history. Understanding events like supervolcanic eruptions, anoxic oceans, or asteroid impacts requires more than imagination. It requires precise instruments, meticulous records, and careful interpretation. Among the most powerful of these tools are isotopic analysis, sedimentary records, and drill cores, each unlocking a different facet of our planet's story. Imagine standing on the edge of a cliff, looking down at layers of rock laid down over millions of years. These layers are Earth's diary, each stratum preserving clues about climate, life, and environmental changes. Sedimentary rocks record everything from volcanic ash and ocean chemistry to fossilized remains of plants and animals. Geologists and paleoclimatologists study these records to reconstruct ancient events with astonishing detail. Picture them carefully noting variations in color, grain size, and composition, every detail a potential clue to Earth's past. One of the most revealing tools in this exploration is isotope analysis. Isotopes are variants of elements with different numbers of neutrons, and they behave slightly differently in chemical and physical processes. By measuring ratios of stable isotopes, such as carbon-12 carbon-13 or oxygen-16 to oxygen-18, scientists can infer ancient temperatures, ocean circulation patterns, and even the productivity of ecosystems. Imagine tiny variations in the chemical makeup of a shell or a mineral crystal revealing climate conditions from millions of years ago. As if the Earth itself had left messages encoded in matter. Sedimentary records complement isotopic studies. Layers of sediment accumulate slowly over time, forming sequences that capture environmental change. For example, black shales often indicate low oxygen conditions, while limestone can reveal warm, shallow seas filled with marine life. Each layer is a snapshot of a specific time, allowing scientists to read Earth's history chronologically, much like flipping through a very long and detailed photo album. Picture rivers, lakes, and oceans depositing minerals and organic matter year after year, silently documenting the story of life, climate, and geological events. Drill cores provide a more direct and tangible glimpse into the past. By drilling into the seafloor, continental crust, or ice sheets, scientists extract long cylindrical samples that preserve sediments, fossils, and chemical signatures from thousands to millions of years ago. Imagine holding a drill core in your hands. The varying colors, textures, and inclusions tell a story of environmental shifts, catastrophic events, and gradual transformations. Layers of volcanic ash within a core can indicate past eruptions, while tiny fossilized organisms reveal oceanic conditions and extinction events. Drill cores are, in essence, time capsules, allowing us to examine history layer by layer, combining these tools. Scientists have reconstructed events like the Permian-Triassic extinction, KPG asteroid impact, and Paleocene-Eocene thermal maximum. Isotopes reveal temperature and carbon cycle changes. Sediments show environmental stress, and drill cores provide precise chronological markers. Imagine an intricate puzzle where each tool provides a critical piece. Without isotopes, the timeline may be unclear. Without sediments, the context is missing. Without cores, the evidence is incomplete. Together, they form a robust picture of Earth's dynamic history. The process of analysis is both methodical and creative. Scientists must interpret indirect evidence, differentiate between local and global signals, and account for post-depositional changes. For example, isotopic signatures may be altered by chemical reactions long after deposition, requiring careful calibration and cross-referencing with multiple lines of evidence. Picture a detective piecing together a crime scene from subtle clues, each requiring patience, precision, and insight to understand the narrative. Drill cores also allow for high-resolution studies of recent history, revealing decadal, centennial, and millennial climate variations. Ice cores, for example, trap bubbles of ancient atmosphere, letting scientists measure greenhouse gas concentrations over hundreds of thousands of years. Sediment cores from oceans capture fluctuations in productivity, temperature, and oxygen levels. By examining these cores, we can place events like the Toba eruption, anoxic oceans, or supervolcanic episodes in a precise chronological context. Imagine slowly unwrapping a timeline of Earth's life and climate. Each centimeter of core a step further back in time. These tools not only illuminate the past, but also guide our understanding of the present and future. By studying how Earth responded to extreme events, temperature spikes, oxygen loss, asteroid impacts, we gain insights into resilience, recovery, and vulnerability. Such knowledge is essential for predicting how modern ecosystems and human societies might respond to ongoing climate change. Ocean deoxygenation and potential cosmic threats. Imagine translating millions of years of geological history into lessons for our own survival and planning. The beauty of these scientific tools lies in their ability to connect micro and macro scales. Tiny isotopic variations or microscopic fossils reveal planetary scale processes, linking chemical changes to global climate events, mass extinctions, and evolutionary milestones. Each discovery adds a chapter to the story of Earth, building a coherent narrative from the seemingly chaotic record of rocks, sediments, and ice. Imagine the world as a living archive, waiting for careful eyes and precise instruments to read its hidden tales. As you relax and visualize this story, picture scientists in the field carefully sampling rocks, drilling cores, and analyzing isotopes. Imagine the intricate interplay between observation, measurement, and interpretation. Each piece of evidence is a whisper from the past, telling us about climates, oceans, and catastrophic events. Let your mind drift through the layers of time, through sediments, isotopic signals, and cores, absorbing the quiet yet profound testimony of Earth's long history. Finally, as you settle into calm reflection, consider the elegance of these tools. Isotopes reveal invisible changes. Sediments record the passage of time, and drill cores preserve tangible samples from deep history. Together, they allow us to explore millions of years of Earth's story, understanding both its crises and its recoveries. As you breathe slowly and gently, imagine the Earth speaking through these layers, whispering tales of survival, catastrophe, and resilience, guiding your mind toward rest, wonder, and peaceful reflection. Traces in today's climate and ecosystems. Now, we shift our focus from the distant past to the subtle echoes of Earth's ancient crises in the present day. While we have explored catastrophic events such as supervolcanoes, asteroid impacts, anoxic oceans, and genetic bottlenecks, it is fascinating to consider how these episodes continue to shape today's climate, ecosystems, and even human society. In this part, we will trace the lingering signals of these events, allowing us to connect deep time with the world we inhabit now. Imagine walking along a coast, observing the waves and the currents, or standing in a forest, listening to birds and the rustle of leaves. Hidden beneath these familiar landscapes are records of past extremes. The ocean's atmosphere and land all carry subtle markers left by ancient upheavals. Oxygen levels, sediment compositions, isotopic ratios, and fossil distributions all contain clues, acting as messengers from the past, whispering about catastrophic events that occurred millions or even billions of years ago. One clear example of these traces is the ongoing influence of ancient volcanic activity. Large igneous provinces, such as the Siberian traps or Deccan traps, not only caused mass extinctions but also altered Earth's climate for millennia. The carbon dioxide and sulfur dioxide released by these eruptions warmed the atmosphere or triggered acid rains, impacting ecosystems on a global scale. Today, we can still detect elevated levels of carbon isotopes in rock layers formed during these periods, revealing the profound legacy of ancient volcanism on Earth's carbon cycle. Imagine these chemical fingerprints as invisible threads linking deep history to modern environmental chemistry. Another connection lies in oceanic oxygen levels. Ancient anoxic events, when vast regions of the oceans lost oxygen. Prefigured phenomena we observe today in some coastal areas and large lakes. Modern dead zones form, where nutrient runoff and warming create oxygen-depleted waters, mimicking ancient crises on a smaller scale. These zones impact fisheries, biodiversity, and carbon cycles, reminding us that Earth's systems are dynamic, interconnected, and still vulnerable to perturbations. Imagine vast stretches of water where life struggles to survive, a quiet echo of deep time resonating in our contemporary oceans. Similarly, genetic bottlenecks and evolutionary pressures from past events influence modern biodiversity. Species that survived ancient catastrophes often carry adaptations that reflect their turbulent history. For example, modern corals, fish, and plants may bear genetic signatures of surviving oceanic anoxia, extreme temperature shifts, or volcanic winters. These adaptations help species endure environmental stress, illustrating the resilience built over millions of years. Picture the subtle resilience encoded in DNA, a legacy of surviving crises long before humans appeared. Climate signals also remain embedded in ice cores, tree rings, and sediment layers, allowing scientists to detect patterns reminiscent of past extremes. Episodes like the Paleocene thermal maximum or the PET provide a precedent for rapid warming events. By examining carbon isotopes, temperature proxies, and fossilized microorganisms, we can see how ecosystems responded to sudden environmental stress. Today, these signals inform climate modeling, helping us anticipate the consequences of modern anthropogenic climate change. Imagine ancient events acting as a natural laboratory, offering lessons for navigating current challenges, even modern extreme. Weather patterns may bear subtle traces of Earth's deep history. Changes in ocean circulation, atmospheric composition, and continental arrangements influence the frequency and intensity of storms, droughts, and rainfall distribution. While human activity accelerates climate change today, the planet's baseline response is informed by millions of years of geological and biological adaptation. Think of it as Earth remembering past events, responding through cycles of resilience, adaptation, and recovery. Fossilized ecosystems also provide insight into the long-term stability and fragility of biomes. For instance, reefs, forests, and wetlands often emerge in locations where ancient conditions supported life. Conversely, regions repeatedly impacted by mass extinctions, volcanism, or glaciations may show lower long-term biodiversity. By studying these patterns, we gain perspective on how past extremes constrain or enable life today. Imagine stepping into a forest, realizing that every tree, plant, and animal is shaped by millions of years of environmental trials, survival, and adaptation. Moreover, the human story is intertwined with these traces. Ancient volcanic winters, genetic bottlenecks, and climatic shifts influenced migration, adaptation, and cultural development. Understanding these signals enriches our comprehension of human evolution, resilience, and vulnerability. Imagine early humans observing seasonal shifts, resource scarcity, and climate unpredictability, guided by knowledge inherited from countless generations that survived previous catastrophes. Today, our ability to read geological and ecological signals continues this tradition, allowing us to anticipate challenges and mitigate risks. Finally, as you listen, picture the planet as a living archive, with every ocean current, wind pattern, and sediment layer carrying echoes of past crises. The world around us is not static. It is a reflection of millions of years of dynamic processes, a continuum of change, recovery, and adaptation. Every ecosystem, from the deepest oceans to the tallest forests, bears the subtle fingerprints of Earth's turbulent history, guiding life and influencing climate patterns even today. As you drift into calm reflection, consider this: the traces of ancient events, volcanic eruptions, asteroid impacts, anoxic oceans, and genetic bottlenecks remain embedded in our world. They whisper of crises endured, resilience achieved, and life's persistent ability to adapt. Allow your mind to move through time, following the invisible signals that link the past to the present, and find comfort in the knowledge that life, in its many forms, continues to endure, adapt, and flourish. Now, as we approach the final segment of our journey through Earth's most dramatic and terrifying events, it is time to reflect on the lessons these stories offer us. From global ice ages to supervolcanic eruptions, asteroid impacts, anoxic oceans, and genetic bottlenecks, each episode is a testament to the resilience of life. In this closing part, we will explore the enduring lessons of survival, adaptation, and reflection, and provide guidance for further reading, study, and curiosity. Imagine standing at the edge of a cliff, looking over the vast expanse of time. Every layer of rock, every sedimentary formation, every fossil and isotopic record tells a story of life facing extreme challenges and emerging, often transformed, on the other side. These stories are not merely historical, they are instructive. They teach us about adaptation, resilience, patience, and the subtle interconnectedness of all life and environments. Life has endured, not by strength alone, but by flexibility, innovation, and the ability to respond to sudden change. The first lesson is the importance of resilience in the face of uncertainty. Events like the cryogenian snowball Earth, the Permian-Triassic Great Dying, or the Toba supereruption remind us that life often persists under extreme conditions, sometimes with dramatic reductions in population or diversity. Humanity today faces its own challenges, from climate change to environmental degradation. By studying how life has historically adapted to catastrophic stress, we gain insight into how we might navigate modern crises. Imagine observing early ecosystems recovering from mass extinction, slowly regaining balance, teaching us that recovery is possible even after immense disruption. The second lesson is the value of diversity and redundancy. In both ecosystems and human societies, diversity increases resilience. Genetic bottlenecks illustrate what happens when diversity is drastically reduced. Adaptability diminishes, vulnerability increases. Conversely, in species and communities where diversity remains rich, recovery and innovation are more likely. Think of it as an evolutionary insurance policy. The wider the range of traits and strategies, the better the chance of surviving unpredictable challenges. The third lesson is the power of observation and knowledge. Scientific tools like isotopic analysis, sedimentary records, and drill cores allow us to read the story of Earth, connecting the past to the present. Observation, measurement, and curiosity are vital not just in science, but in daily life. By understanding patterns, predicting risks, and learning from history, we equip ourselves with tools to respond wisely to current and future challenges. Imagine every discovery as a flashlight in the dark, illuminating the path forward through uncertainty. A fourth lesson lies in interconnectedness. Catastrophic events rarely affect only one species or region. They ripple through ecosystems, oceans, atmosphere, and human societies. Recognizing these connections is critical. Modern environmental issues, climate change, biodiversity loss, ocean deoxygenation reflect the cumulative impact of many small and large changes, just as ancient events did. By seeing the links between action, consequence, and adaptation, we cultivate responsibility and foresight. Picture a web of life stretching across time and space. Each thread connected, fragile yet resilient. Each organism a participant in the unfolding story. Fifth, we learn that adaptation often requires innovation and cooperation. Human ancestors survived supereruptions, ice ages, and environmental upheavals not merely by luck, but by sharing knowledge, cooperating in groups, and inventing tools and strategies. These behaviors are encoded in our evolution and remain central to how societies endure today. Imagine small communities strategizing, sharing food, developing fire techniques, or migrating to safer zones. Each action, a testament to the creative capacity that underpins survival. Finally, these lessons inspire humility and wonder. The planet has endured events that dwarf human experience. From asteroid impacts that erased entire species to oceanic anoxia that reshaped marine life. Yet, life, in its persistence and adaptability, remains awe-inspiring. Observing the vast timeline of Earth teaches perspective. Our challenges, though significant, are part of a much larger story, one that underscores both the fragility and resilience of existence. Imagine standing quietly, breathing deeply, and contemplating the layers of time beneath your feet, knowing that you are part of a lineage that has survived unimaginably harsh conditions. For those inspired to learn more, there are countless resources to explore. Books such as The Earth After the Dinosaurs by Sean B. Carroll, The Ends of the World by Peter Brannan, and Life on a Young Planet by Andrew H. Knoll provide detailed accounts of Earth's ancient crises and recoveries. Scientific journals and online databases, including Nature, Science, and Geology, offer the latest research in paleoclimatology, volcanology, and evolutionary biology. Museums, documentaries, and lecture series also provide immersive ways to engage with these topics. Imagine delving into these resources, letting your curiosity wander through time, and connecting with the scientists and explorers who uncover Earth's hidden history. As you let your thoughts drift, consider a personal reflection. The story of Earth is also a story of human potential. By observing, learning, and adapting, we not only understand the past, but also shape the future. Lessons from mass extinctions, supervolcanic eruptions, asteroid impacts, and ancient climates illuminate strategies for resilience, innovation, and cooperation. Let these lessons guide your perspective on modern life, inspiring patience, curiosity, and thoughtful engagement with the world around you. As you begin to relax and settle into quiet reflection, allow your mind to absorb the rhythms of survival, adaptation, and recovery. The Earth teaches us through its layers: fossils, sediments, isotopes, and events. Listen to the whispers of time. They tell of struggle, persistence, innovation, and the enduring resilience of life. As you drift into calm, let the story of Earth's dramatic past guide your thoughts gently into rest, comforted by the knowledge that life, including humanity, has survived against extraordinary odds and continues to endure, adapt, and thrive.